Hello there, and welcome to Science for Sleep, where curiosity gets cozy and science takes the long, gentle road toward rest. Tonight we're going to drift together through a universe that is far larger, quieter, and more crowded than it first appears, because scattered across the dark between stars are worlds that might, just might, be able to host something like life. Not bustling cities or waving forests, at least not that we know of, but places where water could flow, skies could form, and chemistry might take its slow, patient steps towards something alive. Before we set off, let me ask you something simple and personal. Where are you listening from right now? Is it late evening, early morning, or somewhere in between? Maybe there's a lamp glowing softly nearby, or the light from a screen fading as the room grows darker. It's a small moment, but it's yours, and in a strange way, it connects you to every other listener scattered across this spinning planet, each of us tucked into our own little corner of time and space. If you find this journey calming, or if the idea of wandering through distant solar systems helps your thoughts slow down after a long day, you're always welcome to like the video or subscribe. It helps this quiet corner of science reach others who might be looking for a gentle place to rest their mind too. Now, let's ease into the story, because tonight isn't about rushing from one discovery to the next. It's about taking our time and letting the scale of the universe stretch out around us. Imagine for a moment that you're standing outside on a clear night. The air is cool, and the sky is dark enough that the stars feel close, like tiny pinpricks in a vast, soft blanket overhead. Each of those points of light is a sun. Some are bigger than ours, some are smaller, cooler, dimmer. And around many of them we now know planets are quietly circling, unseen by the naked eye, keeping their steady paths through the dark. For most of human history, those stars were just lights, beautiful, mysterious, unreachable. People told stories about them, used them to navigate oceans, and wove them into myths about gods and heroes. The idea that each star might have its own family of worlds was more poetry than science. It was something you could wonder about, but not something you could test. That changed only recently, in the grand timeline of things. In the last few decades, we've gone from not knowing whether planets existed beyond our solar system at all, to cataloguing thousands of them. Rocky ones, gassy ones, hot ones, cold ones, and a small, very special group that fall into a category scientists like to call potentially habitable. That phrase doesn't mean these planets are definitely alive or even comfortable. It simply means they meet a few basic conditions that make life, at least the kind we understand, possible. The most famous of those conditions is the presence of liquid water. On Earth, water is the quiet hero behind every living thing. It dissolves chemicals, carries nutrients, and creates the environment where complex molecules can meet, combine, and slowly become more than the sum of their parts. So when astronomers look at a distant world, one of the first questions they ask is whether it might be warm enough, but not too warm, for water to exist as a liquid on its surface. This idea leads us to something called the habitable zone, sometimes nicknamed the Goldilocks zone, because it's the region around a star where a planet's temperature could be just right. Not so close that its oceans would boil away into steam, and not so far that everything would freeze solid into a shell of ice. Our own Earth sits comfortably in this zone around the Sun, which is one of the reasons life had the time and stability it needed to take hold here. But stars come in many different sizes and personalities. Some burn hot and bright, pouring out enormous amounts of energy. Others glow softly, barely warming the space around them. That means the habitable zone isn't a fixed distance. Around a bright, powerful star, it lies far out. Around a small, cool star, it huddles in close. As our telescopes and techniques improved, astronomers started to notice tiny dips in starlight. A star would shine steadily, then dim just a little, then brighten again. That tiny flicker was often caused by a planet passing in front of the star, blocking a small fraction of its light. By measuring how often this happened and how much light was blocked, scientists could estimate the planet's size and its distance from the star. With enough observations, a picture began to form. There were worlds out there roughly the size of Earth, orbiting at distances that placed them in their star's habitable zone. Each one became a quiet entry in a growing list, a kind of cosmic guestbook of places that might, under the right circumstances, be able to host something living. One of the early names on that list was a planet called Kepler-22b. It was discovered in 2011 by NASA's Kepler Space Telescope, a mission designed specifically to look for those telltale dips in starlight. Kepler-22b orbits a star somewhat similar to our Sun, about 600 light-years away. It's a bit larger than Earth, what scientists call a super-Earth, and it sits comfortably in the habitable zone of its star. We don't know what its surface looks like. It could be a water world, covered in deep global oceans. It might have thick clouds hiding everything below, or it could be something entirely different, a place where the rules we're familiar with don't quite apply. Still, its discovery was a milestone. It showed that planets in the right place, around the right kind of star, weren't rare, distant dreams. They were real, measurable, and waiting to be found. As the years went on, more names joined the list. Kepler-22b, sometimes called Earth's older cousin, because it orbits a star similar to the Sun, but one that's a bit older and brighter. This planet is also slightly larger than Earth and sits in the habitable zone, though closer to the inner edge. If it has water, it might be in a warmer, perhaps more humid state, like a tropical world that never quite cools down. Then there's Proxima Centauri b, a planet orbiting the star closest to our own solar system. Proxima Centauri is a red dwarf, a small cool star that glows much more faintly than the Sun. Its habitable zone lies very close in, and Proxima b orbits so near to its star that a year there lasts only about 11 Earth days. Because it's so close, there's a good chance the planet is tidally locked, meaning one side always faces the star, bathed in constant daylight, while the other side remains in perpetual night. Between those two extremes might be a narrow band of twilight, a region where temperatures could be more moderate. It's a strange picture, but not necessarily an impossible one for life. Red dwarfs like Proxima Centauri are actually the most common type of star in our galaxy. That alone makes them fascinating, because if even a small fraction of the planets around them are habitable, the number of potentially life-friendly worlds could be enormous. At the same time, red dwarfs can be temperamental. They often produce powerful stellar flares, bursts of radiation that could strip away a planet's atmosphere or bathe its surface in harmful energy. So with every promising discovery comes a quiet list of questions. Does the planet have an atmosphere? Is it thick enough to protect the surface? Does the star's activity make the environment too harsh? Or could life, if it ever started, find a way to adapt? One of the most captivating systems we've found so far is called TRAPPIST-1. It's a small, cool star about 40 light-years away, and around it orbit 7 rocky planets, all packed into a space smaller than the orbit of Mercury around our Sun. Of those 7, at least 3 sit in the star's habitable zone. The idea of multiple potentially habitable worlds in one system is almost dizzying. If you stood on the surface of one of those planets, the others would appear large and bright in the sky. Sometimes bigger than our moon appears to us. Nights there might be filled with the slow, steady movement of neighbouring worlds, each one a reminder that this little star hosts not just one, but a whole family of planets that could, under the right conditions, support liquid water. Beyond these headline discoveries, there's a quieter, longer list that keeps growing. Planets like LHS 1140b, a dense, rocky world orbiting another red dwarf, thought to have a thick atmosphere and possibly a global ocean beneath an icy surface, or TWI 700d, an Earth-sized planet in the habitable zone of a small, cool star about 100 light-years away. Each name on the list represents years of work, careful measurements, and cautious interpretation. Astronomers are careful not to oversell what they find. Potentially habitable doesn't mean friendly, it doesn't mean Earth-like in the way we often imagine, with blue skies and green landscapes. It simply means the basic conditions might allow for water and chemistry to do their quiet work. And then there are the planets that blur the lines between categories. Some are larger than Earth, but smaller than Neptune, worlds with thick atmospheres of hydrogen and helium, possibly hiding warm oceans beneath layers of gas. Others might be entirely ocean, with no continents at all, just endless water under a sky we can only guess at. When you step back and look at the big picture, it becomes clear that our solar system is just one small example of what's possible. The galaxy contains hundreds of billions of stars, and current estimates suggest that many of them have planets. Even if a tiny percentage of those planets fall into the potentially habitable category, the number of such worlds could be staggering. Yet, despite all these discoveries, every single one of these planets remains point of light and data. We don't have images of their surfaces. We don't have samples of their air or soil. What we have are careful measurements of how they tug on their stars, how they dim starlight, and how their atmospheres, if they have them, filter the light passing through during a transit. That filtered starlight is one of the most exciting tools astronomers have. By splitting it into its component colours, they can look for the fingerprints of different molecules: water vapour, carbon dioxide, methane, oxygen. Each one leaves a subtle mark in the spectrum, a hint of what the planet's atmosphere might be made of. In recent years, new telescopes have begun to push this technique further. They can study smaller planets and fainter stars, looking for ever more delicate signals. It's slow work, and often the results raise more questions than answers, but with each observation, the picture becomes a little clearer. As you listen to all of this, it might be tempting to think of these worlds as destinations, places we might one day visit or even settle. For now, though, they are more like stories. Each one is a chapter in our growing understanding of what planets can be and where life might find a foothold. What's remarkable is not just that these planets exist, but that we, on a small rocky world orbiting an average star, have learned how to detect them at all. The light that reveals their presence has travelled for years, decades, sometimes centuries, crossing empty space before it reaches our telescopes. By the time we notice a planet's shadow in that light, the world itself has already moved on, continuing its quiet orbit around its star. There's something gently humbling about that. We're always looking at the past, even as we try to imagine the future. Every potentially habitable planet we've found so far is both a real place and a kind of time capsule, a snapshot of a moment long gone. As this list continues to grow, it changes how we think about our own world. Earth stops feeling like a singular miracle and starts to feel like one example among many, perhaps a particularly successful one, but not necessarily unique. That doesn't make our planet less special. If anything, it makes it more precious, because we know just how narrow the conditions for comfort and stability can be. Somewhere out there, around a small red star or a bright yellow sun, a rocky world might be experiencing its own quiet evening. Its sky might be darkening, or perhaps glowing softly under a constant twilight. If life exists there, it would be going about its own rhythms, unaware that, across the vast distance of space, a species on another planet is slowly, patiently learning how to notice its home. We've only just begun this exploration. The planets we've found so far are the easy ones, the ones that make the biggest dips in starlight or tug most strongly on their stars. As our tools improve, smaller and more Earth-like worlds will come into view, filling in the quieter, more subtle parts of the cosmic map. So for now, we hold this growing collection of potentially habitable planets as a promise rather than a conclusion. A promise that the universe is richer and more varied than we once imagined. A promise that the story of life might not be confined to a single pale blue dot. To talk about what it really means for a world to be habitable, it helps to let go of the picture most of us carry around in our heads. When we hear the word habitable, we often imagine something that looks comfortably familiar. Blue skies, liquid oceans, maybe something green growing along the edges of a shoreline. A place where you could, at least in theory, Step outside without a spacesuit and take a deep breath. But for scientists, the idea is both simpler and far more open-ended than that. At its core, a habitable world is not one that looks like home. It is one that offers the basic conditions needed for chemistry to become interesting. That might sound like a modest goal, but it is actually a profound one. Because once chemistry becomes interesting, it has a habit of getting complicated, and given enough time, that complexity can sometimes turn into something that reacts, adapts, and eventually, in our own case, wonders about the stars. The first piece of this puzzle is temperature. Not in a cozy human sense, but in a molecular one. Most of the life we know relies on chemical reactions that take place in liquid water. If things are too cold, everything freezes into a rigid, unmoving lattice. Molecules get stuck, reactions slow down to a crawl. If things are too hot, water turns to vapor, and complex molecules start to break apart. So there is a broad middle range where water can stay liquid, and where chemistry can quietly go about its business. This is where the idea of the habitable zone comes back into the picture, but now with a bit more nuance. The habitable zone is not a narrow ring where everything outside it is dead, and everything inside it is alive. It is more like a rough guideline, a region where, given the right conditions, a planet could maintain liquid water on its surface. Those right conditions include more than just distance from a star. A planet's atmosphere plays a huge role. On Earth, our atmosphere acts like a blanket, trapping heat and keeping the surface warmer than it would be if our planet were just a bare rock in space. This is known as the greenhouse effect, and without it, Earth would be a frozen world, even though it sits comfortably in the Sun's habitable zone. So when astronomers look at a distant planet and decide it might be habitable, what they're really saying is that, based on its orbit and the kind of star it circles, it could, in theory, have an atmosphere that keeps it warm enough for liquid water. That is a lot of could and in theory, and that uncertainty is part of what makes this field both cautious and exciting. Atmospheres are not guaranteed. A planet might start out with one and lose it over time. Strong stellar winds can strip away gases, especially around small, active stars. Low gravity can make it hard for a planet to hold onto its air in the first place, so part of habitability is not just having an atmosphere but keeping it. Then there is the question of what that atmosphere is made of. On Earth, nitrogen and oxygen dominate, with small but important amounts of carbon dioxide, water vapor, and other gases. Each of these plays a role in regulating temperature and supporting life as we know it. On another planet, the mix could be very different. A thick blanket of carbon dioxide might create a runaway greenhouse effect, turning the surface into something more like Venus, where temperatures are hot enough to melt lead. A thin, wispy atmosphere might fail to trap heat at all, leaving the surface cold and barren. Water itself is a bit of a special case. We often talk about liquid water as if it is the universal key to life, and in many ways, that is because it is the only example we have. On Earth, every living thing depends on it. It is a remarkable solvent. It allows a wide range of chemicals to dissolve, move around, and interact. It remains liquid over a relatively wide range of temperatures. It expands when it freezes, which helps keep bodies of water from freezing solid from the bottom up. But it is worth remembering that this is a very Earth-centered view. It is possible that life elsewhere could use a different liquid as its medium. Scientists have speculated about ammonia-based life, or even life that uses liquid methane or ethane, like the lakes found on Saturn's moon Titan. These environments would be far colder than anything we would consider comfortable, but chemistry does not mind being uncomfortable. Still, when astronomers say a planet is potentially habitable, they usually mean habitable for life that is at least somewhat similar to ours. Life that needs liquid water, moderate temperatures, and a stable environment over long periods of time. Stability is another quiet but crucial ingredient. Life, especially complex life, does not appear overnight. On Earth, it took hundreds of millions of years for the first simple organisms to appear, and billions more for multicellular life to develop. That means a habitable world needs not just the right conditions, but the right conditions for a very long time. This is where the nature of the star becomes important again. Stars change over time. Our Sun, for example, has slowly grown brighter over billions of years. In the distant future, it will become so bright that Earth's oceans will eventually boil away. For now, though, it is in a stable phase of its life, quietly fusing hydrogen into helium and providing a relatively steady output of energy. Some stars are not so well behaved. Young stars, especially small red dwarfs, can be highly active. They produce frequent flares, bursts of radiation that can flood nearby planets with high-energy particles. Over time, this can erode atmospheres and damage the chemistry on a planet's surface. A world in the habitable zone of such a star might have the right temperature, but still be a very harsh place. On the other end of the spectrum, very large stars burn through their fuel quickly. They shine brightly, but they do not last long. A planet in the habitable zone of a massive star might only have a few 100 million years before its sun changes dramatically or dies altogether. That might not be enough time for life to get started and evolve into anything complex. So when scientists talk about a planet being potentially habitable, they are also thinking about whether its star is likely to provide a long, steady window of opportunity. A calm, middle-aged star like our Sun is, in that sense, a very good landlord. Another factor that often goes unnoticed is a planet's own internal activity. Earth is not just a static ball of rock. It has a molten interior, moving tectonic plates, and a magnetic field generated by the motion of liquid iron in its core. All of these play roles in habitability. Tectonic activity helps recycle carbon and other elements between the atmosphere, the surface, and the interior. This is part of what keeps Earth's climate relatively stable over long timescales. If carbon dioxide builds up in the atmosphere, weathering processes can pull it out of the air and lock it into rocks. Volcanic activity can then release it back into the atmosphere. This slow geological thermostat helps prevent Earth from becoming too hot or too cold. A magnetic field, meanwhile, acts like a shield. It deflects charged particles from the solar wind, protecting the atmosphere and the surface from being stripped away or bombarded with radiation. Mars is often used as an example here. It likely had a thicker atmosphere and liquid water on its surface billions of years ago, but it lost its magnetic field, and over time the solar wind gradually eroded its atmosphere, leaving it cold and dry. So a truly habitable world might need not just the right distance from its star and the right kind of atmosphere, but also a warm, active interior and a strong magnetic field. That is a long list of requirements, and it helps explain why Earth feels so finely tuned. Yet, the universe is very large, and it has had a lot of time to experiment. Even if a small fraction of planets meet all these conditions, that could still mean millions or billions of potentially habitable worlds in our galaxy alone. There is also the question of what surface means. When we talk about habitable planets, we often picture life living on the surface, under a sky. But in our own solar system, some of the most promising places for life are hidden beneath layers of ice. Moons like Europa, which orbits Jupiter, and Enceladus, which orbits Saturn, are thought to have global oceans beneath their frozen crusts. These oceans are kept liquid by tidal heating, the constant flexing of the moon's interior caused by the gravity of the planet it orbits. In these dark, hidden seas there is no sunlight. Any life that exists there would have to rely on chemical energy, perhaps from hydrothermal vents on the ocean floor, much like some of the most ancient life on Earth does. This expands the idea of habitability beyond just planets in the right place around a star. It suggests that worlds far from the traditional habitable zone could still host life, as long as they have a source of energy in liquid water somewhere inside. When astronomers look at exoplanets, they cannot yet see these kinds of hidden oceans directly, but the idea changes how they think about what might be possible. A planet that looks too cold on the surface might still be warm and wet below. A world that seems hostile from a distance might be quietly hospitable in ways we have not learned to detect yet. Energy, in a broader sense, is another key part of habitability. Life needs a way to power its chemistry. On Earth, most life ultimately depends on sunlight, either directly through photosynthesis or indirectly by eating things that do. But sunlight is not the only option. Chemical energy, such as that released by reactions between water and certain types of rock, can also support ecosystems. This means that a planet or moon does not necessarily need to be bathed in light to be considered potentially habitable. It needs a steady source of energy that can drive chemical reactions over long periods of time. Then there is the element of chance. Even if a world has all the right ingredients, life might not start. Or it might start and then be wiped out by a catastrophic event, like a massive impact or a period of intense stellar activity. On Earth, life has been remarkably resilient, surviving mass extinctions, climate swings, and dramatic changes in the planet's surface. But there is no guarantee that this kind of persistence is universal. When scientists compile lists of potentially habitable planets, they are not making promises. They are highlighting opportunities. Each planet on the list is a place where the story of life could, in theory, unfold. Some might be barren. Some might host only simple, microbial life. A very small number perhaps might be home to something more complex. From our current vantage point, all of these possibilities look the same. A faint dip in starlight, a subtle wobble in a star's motion, a spectrum with a few suggestive lines. It is a bit like trying to understand a distant city by looking at its silhouette on the horizon. You can see that something is there, but not what is happening in the streets. This is why new telescopes and missions are so eagerly anticipated. They promise to move us from silhouettes to hints of detail, to atmospheres instead of orbits, to chemistry instead of just size and distance. The idea of habitability is also evolving as we learn more about extreme environments on Earth. In the past few decades, scientists have discovered life in places that once seemed completely inhospitable. Bacteria living in boiling hot springs, microbes buried deep in the Earth's crust, surviving without sunlight for millions of years, organisms thriving in highly acidic or highly salty environments. These discoveries have expanded our sense of what life can tolerate. They suggest that if life does start somewhere, it can be surprisingly adaptable. That does not mean it can survive anywhere, but it does mean that the line between habitable and uninhabitable is not as sharp as we once thought. So when you hear about a potentially habitable planet, it can help to imagine it not as a second Earth, but as a question. A place where conditions might allow chemistry to take a step beyond the ordinary. A world that could, under the right circumstances, develop its own version of a living system, shaped by its own star, its own geology, and its own history. There is something quietly powerful about that idea. It takes the focus off finding a mirror of ourselves and places it on understanding the range of what is possible. Each new planet adds another data point to a very old, very human question. Are we alone? Or is the universe quietly full of stories we have not yet learned how to read? As we keep adding to the list of potentially habitable worlds, the definition itself continues to shift. It becomes less about ticking off a checklist and more about recognizing a spectrum of environments, each with its own balance of challenges and opportunities. Some worlds might be on the edge of being too hot or too cold. Others might have thick atmospheres that create high surface pressures. Some might orbit stars that flare and calm in long cycles. Each one represents a different experiment in planetary living conditions. In that sense, habitability is not a single state. It is a range, a sliding scale between clearly hostile and clearly welcoming, and most of the worlds we have found so far sit somewhere in the middle, leaning one way or the other, but never revealing all their secrets at once. As you let this idea settle in, it can be strangely calming. The universe is not a simple place with a single template for life. It is a vast collection of environments, each one shaped by a delicate interplay of physics, chemistry, and time. Somewhere among them, perhaps many places among them, those conditions line up just right for something living to take hold. We do not yet know how often that happens, or what it looks like when it does, but with every new planet added to the list, the question becomes a little less abstract and a little more grounded in real, measurable worlds. Before we can really make sense of all those distant worlds, the ones that show up as tiny dips in starlight and faint signals in data charts, it helps to turn our attention back to the place we know best. Not because Earth is the standard by which everything else must be judged, but because it is the only example we have where we can walk around, scoop up a handful of soil, breathe the air, and know for certain that life is not just possible but everywhere. In a quiet way, Earth is our training ground. The one planet where we can study habitability from the inside out, rather than from millions of kilometers away. It is easy to forget how unusual our world actually is, because it is the background of our lives. The sky looks blue because of the way our atmosphere scatters sunlight. The ground feels solid under our feet. Water falls from the sky, flows into rivers, pools in oceans, and then rises again into clouds. These things feel ordinary, almost automatic. But when you start to think about them in the context of a universe filled mostly with empty space, blazing stars and frozen or overheated rocks, they begin to look more like a delicate balancing act than a default setting. One of the most basic features of Earth is its size. Our planet is large enough to hold onto an atmosphere, but not so large that it became a gas giant. Gravity here is strong enough to keep nitrogen, oxygen, and water vapor from drifting off into space over billions of years. At the same time, it is gentle enough that those gases can circulate, forming winds, clouds, and weather patterns that move heat and moisture around the globe. This balance is not guaranteed on every rocky world. Smaller planets, like Mars, struggle to keep their air. Larger ones may hold on to thick, heavy atmospheres that create crushing pressures at the surface. Distance from the Sun is another part of the picture, but even that simple fact hides a lot of complexity. Earth orbits at an average distance of about 150 million kilometers, which places it in a region where sunlight provides enough energy to keep water liquid, but not so much that it drives temperatures to extremes. Yet, this alone would not be enough without the right kind of atmosphere to regulate that energy. On Earth, carbon dioxide, water vapor, and other greenhouse gases trap some of the heat that would otherwise escape back into space. This keeps the average surface temperature higher than it would be on a bare rock at the same distance from the Sun. The result is a climate that, while it can be dramatic and sometimes harsh, stays within a range that life can adapt to. But Earth's climate system does not just trap heat. It also has ways to release it. Clouds reflect sunlight back into space. Ice and snow, which are bright and reflective, help cool the planet when they spread across large areas. Vegetation affects how much carbon dioxide stays in the air. Over long periods of time, rocks weather, oceans absorb gases, and volcanic eruptions release them again. This slow global exchange helps keep the planet from tipping too far in one direction. Then there is the matter of water itself. Earth is often called the blue planet, and from space that description makes perfect sense. About 70% of the surface is covered by oceans. But water on Earth is not just a surface feature. It moves through every layer of the planet's systems. It falls as rain and snow flows into rivers, seeps into the ground, and eventually returns to the sea. It evaporates, forms clouds, and falls again. This constant motion is part of what shapes the landscape, the climate, and the chemistry of the planet. From the perspective of habitability, water's role goes even deeper. It is the medium in which most of Earth's life does its work. Inside every cell, chemical reactions take place in watery solutions. Nutrients are carried in fluids. Waste is removed the same way. Even the structure of many biological molecules depends on how they interact with water. Yet, for all its importance, Earth's water did not have to end up here in the amount and form that it did. There are still debates about how our planet got its water in the first place. Some theories suggest that much of it was delivered by icy asteroids or comets early in Earth's history. Others propose that it was present in the building blocks that form the planet itself. Either way, the result is a world with just enough water to cover vast areas, but not so much that the entire surface is submerged. This balance has consequences. Continents rise above the oceans, creating diverse environments. Coastlines form, where land and sea meet. Rivers carve valleys and carry minerals from the interior to the oceans. These varied settings provide different niches where life can take hold and adapt in countless ways. Another quiet but powerful feature of Earth is its magnetic field. Generated by the movement of molten iron in the planet's outer core, this field extends far out into space, forming a protective bubble around the planet. When charged particles from the Sun, known as the solar wind, reach Earth, many of them are deflected by this magnetic shield. Some are guided toward the poles, where they create the glowing curtains of the aurora. But most are kept from directly hitting the atmosphere and the surface. Without this protection, Earth might look very different. Over long periods of time, the solar wind can strip away atmospheric gases. This is what is believed to have happened to Mars after it lost its own magnetic field. The red planet likely once had a thicker atmosphere and flowing water on its surface. Today it is cold, dry, and exposed to higher levels of radiation. So when we think about Earth as a benchmark for habitability, the magnetic field becomes part of the checklist. A world might have the right temperature and the right distance from its star, but without some kind of shielding, its atmosphere and surface chemistry could be slowly eroded away. Beneath our feet, Earth is also alive in a geological sense. Tectonic plates move, collide, and pull apart. Volcanoes erupt. Mountains rise and wear down. These processes reshape the surface over millions of years, but they also play a role in the planet's long-term climate. By recycling carbon and other elements between the interior, the surface, and the atmosphere, geology helps keep the planet's environment within a range that life can tolerate. This kind of activity depends on heat, left over from Earth's formation, as well as heat generated by the decay of radioactive elements inside the planet. Over time, that heat slowly escapes into space, but for now it is enough to keep the interior dynamic. On smaller planets, this internal heat can fade more quickly, leading to a geologically dead world. Without tectonics or volcanism, the long-term regulation of climate becomes much harder. When we look at Earth from a distance, all of these systems blur together into a single bright blue and white sphere. But up close, it is a complex web of interactions. The atmosphere influences the oceans affect the climate shapes the land and the water support life, and life in turn changes the atmosphere and the surface. This last part is especially interesting because it means that Earth's habitability is not just something that happened to the planet, it is something that life itself has helped maintain. One of the most dramatic examples of this is the presence of oxygen in our atmosphere. For the first half of Earth's history, there was very little free oxygen in the air. Life existed, but it was mostly microbial, and it lived in environments where oxygen was scarce or absent. Then, about 2.4 billion years ago, certain microorganisms began producing oxygen as a byproduct of photosynthesis. Over time, this oxygen built up in the atmosphere, transforming the planet. This change was catastrophic for many of the organisms that had evolved in an oxygen-free world, but it also opened the door for new forms of life that could use oxygen to extract much more energy from their food. Eventually, this led to the complex multicellular life we see today. From a distance, the presence of large amounts of oxygen in a planet's atmosphere could be a sign that something like life is active there. Oxygen is a reactive gas. It does not tend to stick around on its own. On Earth, it is constantly being removed by chemical reactions with rocks and other materials. The reason it remains abundant in the air is that living organisms keep producing it. This is why astronomers are so interested in the idea of biosignatures. These are chemical signs in a planet's atmosphere that might indicate the presence of life. Oxygen is one example. Methane is another, especially if it appears alongside oxygen. On Earth, these two gases coexist in large part because living things keep replenishing them. However, Earth also teaches us caution. There are non-biological ways to produce some of these gases. A planet might have oxygen in its atmosphere because of chemical reactions driven by sunlight, not because of life. So even our own planet as a benchmark does not provide a simple, foolproof test. Looking back through Earth's history also reminds us that habitability is not a fixed state. Our planet has gone through periods that would be very uncomfortable for most of today's life. There have been times when much of the surface was covered in ice, in what are sometimes called snowball Earth events. There have been times of intense volcanic activity when the atmosphere was thick with ash and gas. There have been mass extinctions when a large fraction of species disappeared in a relatively short span of geological time. And yet, through all of this, life has persisted. It has changed, adapted, and diversified. This resilience suggests that once life gets a foothold on a planet, it can be remarkably hard to completely erase. That does not mean it is guaranteed. A large enough impact, a runaway greenhouse effect, or a dramatic change in a star's behaviour could still make a world truly uninhabitable. But it does mean that habitability and life are not fragile in quite the way we might imagine. From the outside, Earth might not always have looked like an ideal home. A distant observer watching our planet over billions of years would have seen it change colour, brightness, and atmospheric composition. There would have been long stretches when oxygen was absent, when the surface was frozen, or when the climate was far warmer than it is now. And yet, during much of that time, life was already present, quietly doing its work. This perspective can change how we think about potentially habitable exoplanets. A world that looks harsh by our current standards might still be in a phase of its own long story, one where life could exist in forms or places we have not learned to recognize yet. Earth also shows us that location within a solar system matters in more ways than just distance from the star. Our planet has a large moon, which stabilizes its tilt. This tilt, in turn, gives us seasons. Without the moon's gravitational influence, Earth's axis might wobble much more over time, leading to dramatic changes in climate. Some periods could be far colder or far hotter than anything we experience now. The presence of large neighbouring planets, like Jupiter, may also play a role. Jupiter's strong gravity can deflect or capture some asteroids and comets that might otherwise head toward the inner solar system. This does not mean Earth is completely protected, as history shows, but it may reduce the frequency of catastrophic impacts, so even the broader architecture of a planetary system can influence whether a particular world remains stable enough for life to have time to develop and evolve. When scientists look at distant systems, they try to piece together these kinds of details from limited data. They look at how many planets there are, how massive they seem to be, and how their orbits are arranged. They try to infer whether a system might be calm and long-lived, or chaotic and prone to dramatic changes. All of this work is guided in one way or another by what we have learned from Earth. Our planet is not the template that every other world must follow, but it is the only example we can study in full detail. Every rock sample, every ice core, every atmospheric measurement adds another layer to our understanding of how a habitable world can function over deep time. There is also a human element to this benchmark. Earth is not just a scientific reference point, it is home. Every question we ask about other planets is shaped by the fact that we live here. We wonder whether other worlds have skies because we look up at our own. We search for water because we know how central it is to our lives. We think about climate stability because we are experiencing changes in our own. In a way, studying Earth and studying exoplanets are two sides of the same conversation. One looks outward, scanning the galaxy for places that might resemble our home in some essential way. The other looks inward, trying to understand how our home came to be what it is, and how it continues to change. As our tools improve, this conversation becomes more detailed. We can compare the atmospheres of the distant planets to our own. We can look for signs of clouds, temperature differences between day and night, and even hints of weather patterns. Each comparison adds context. Each difference and similarity helps refine what we mean when we say a world might be habitable. There is something quietly grounding about using Earth as this reference point. It reminds us that, for all our technology and all our reach, our perspective is still shaped by one small planet orbiting one ordinary star. The conditions we consider normal or even necessary might be just one way of doing things among many. And yet, Earth's story also offers a kind of hope. It shows that a planet does not need to start out perfect to become a place where life can flourish. It can be battered, reshaped, frozen, and warmed. It can go through long, quiet periods and dramatic upheavals. Through it all, if the basic conditions remain within a certain range, life can find a way to persist. So as we keep our eyes on those distant points of light, measuring tiny changes in brightness and searching for chemical fingerprints in starlight, we carry Earth's example with us, not as a rigid standard, but as a reminder of what a living world can be when a handful of physical and chemical conditions line up, and then are given enough time to play out their slow, complex dance. For a very long time, the night sky felt like a finished picture. Stars were stars, fixed points of light pinned to a vast dark backdrop. Our own solar system, with its familiar lineup of planets circling the sun, felt like a special case, a kind of cosmic island. People wondered, of course, philosophers speculated, writers imagined, but in terms of hard evidence, there was nothing to confirm that any of those distant suns had worlds of their own. So when we talk about the discovery that changed everything, we're really talking about a quiet shift in how humanity sees its place in the universe. Not a single dramatic moment with flashing lights and bold headlines, but a series of careful measurements, patient observations, and gradually growing confidence that the universe was not just full of stars, but full of systems, each with its own collection of orbiting worlds. Before the 1990s, astronomers had plenty of reasons to believe planets around other stars should exist. The physics of star formation suggested that when a star is born from a collapsing cloud of gas and dust, a disk of material naturally forms around it. In that disk, dust grains stick together, grow into rocks, and eventually become planets. Our own solar system fit this model beautifully. There was no obvious reason it should be unique. Yet belief and proof are different things. Stars are incredibly bright compared to the tiny dark planets that circle them. Trying to see a planet directly is like trying to spot a firefly next to a lighthouse from miles away. The glare of the star overwhelms almost everything else. So astronomers had to get creative. Instead of looking for the planets themselves, they started looking for the subtle effects those planets might have on their stars. One of the earliest methods to show real promise was based on a simple idea. A planet and a star do not actually behave like a big object being orbited by a tiny one. In reality, they both orbit a shared centre of mass. The star's motion is much smaller, but it is there. As a planet circles, it tugs gently on the star, causing it to wobble ever so slightly. This wobble affects the light we see from the star. When the star moves toward us, its light is shifted slightly toward the blue end of the spectrum. When it moves away, the light shifts toward the red. This is known as the Doppler effect, the same principle that makes a passing siren change pitch as it moves by. By carefully measuring these tiny shifts in a star's spectrum, astronomers can infer the presence of an orbiting planet. They can estimate its mass and its orbital period, all without ever seeing the planet directly. In the late 1980s and early 1990s, teams of astronomers began applying this technique with increasing precision. The instruments were sensitive, but the challenge was enormous. The changes they were looking for were incredibly small, often just a few meters per second in the star's motion. That is walking speed, measured across light years. Then, in 1992, something remarkable happened. astronomers Alexander Wolszczan and Dale Frail announced the discovery of planets orbiting a pulsar, a rapidly spinning, highly magnetized neutron star left behind after a supernova. These were not the kinds of stars anyone expected to host planets. Pulsars are extreme, violent objects emitting intense radiation. The idea that planets could exist around them was surprising, to say the least. The planets were detected through precise timing of the pulsar's radio pulses, which showed slight variations caused by the gravitational pull of orbiting bodies. This was the first confirmed detection of exoplanets, planets beyond our solar system. It was a stunning result, but it came with a caveat. These were not worlds anyone imagined as potential homes for life. A pulsar is not a gentle, life-giving sun. It is more like a cosmic lighthouse built from the collapsed core of a dead star. The discovery proved that planets could exist elsewhere, but it did not yet answer the more familiar question of whether normal sun-like stars had planets too. That answer arrived just a few years later, in 1995. Swiss astronomers Michel Mayer and Didier Queloz announced the discovery of a planet orbiting a star called 51 Pegasi, about 50 light-years away. This star was very similar to our Sun. The planet they found, however, was nothing like anything in our own system. The planet, later named 51 Pegasi b, was about half the mass of Jupiter, but it orbited extremely close to its star. It completed a full orbit in just over 4 days. That put it so near its sun that its surface temperature would be scorching, far hotter than anything in our solar system. This kind of planet came to be known as a hot Jupiter. It was a gas giant, but instead of forming far from its star as Jupiter did, it was hugging its star tightly. This was unexpected and at first confusing. Planet formation models at the time suggested that gas giants should form in the colder outer regions of a planetary system, where ices can exist and help build up a large core. Finding a giant planet so close to its star meant something else had to be happening. Either these planets formed far out and then migrated inward, or our understanding of how planets form needed to be revised. In a way, this first normal exoplanet discovery did more than just confirm that other stars had planets. It told astronomers that planetary systems could be very different from our own. The solar system was not necessarily the blueprint. It was just one example among many. After 51 Pegasi b, discoveries began to accelerate. Improved instruments and dedicated surveys started to find more planets, often more hot Jupiters at first, because they were easier to detect. Their large masses created strong wobbles in their stars, and their close orbits made those wobbles repeat frequently. But astronomers wanted more than just gas giants. They wanted to find smaller, rocky planets, the kind that might resemble Earth. That required even more sensitivity. Another method began to take center stage, one that would eventually revolutionize the field. This was the transit method. Instead of looking for a star's wobble, astronomers watched for tiny dips in brightness as a planet passed in front of the star from our point of view. This method has a kind of quiet elegance. If a planet's orbit happens to line up just right, it will block a small fraction of the star's light each time it passes between the star and Earth. The amount of dimming tells astronomers the size of the planet relative to the star. The timing of the dips reveals the planet's orbital period. At first, this technique was used from the ground, but Earth's atmosphere makes precise measurements difficult. The real breakthrough came with space-based telescopes designed specifically for this task. In 2009, NASA launched the Kepler Space Telescope. Its mission was simple to describe and challenging to execute. Kepler would stare at a single patch of sky, monitoring the brightness of over 150,000 stars, looking for the telltale dips caused by transiting planets. Kepler's field of view was fixed. It did not sweep across the sky. It simply watched, patiently, night after night, year after year, waiting for patterns to emerge in the data. What it found changed everything. Within a few years, Kepler had identified thousands of planet candidates. Some were confirmed, others remained possibilities, but the sheer number was staggering. Planets were not rare. They were common. In fact, based on Kepler's results, astronomers began to estimate that, on average, every star in the galaxy might have at least one planet. Even more surprising was the diversity of the planets Kepler found. There were worlds larger than Earth but smaller than Neptune, a class of planets that does not exist in our own solar system. There were tightly packed systems where multiple planets orbited closer to their star than Mercury does to the Sun. There were planets in the habitable zones of their stars, raising the first real, data-driven hopes of finding Earth-like worlds elsewhere. Kepler's discoveries turned the search for exoplanets from a niche pursuit into a central part of modern astronomy. The question was no longer whether planets existed around other stars. The question became what kinds of planets existed, how common they were, and what their properties might tell us about the potential for life. As the catalogue grew, so did the methods. Astronomers combined transit data with radial velocity measurements, using one technique to estimate a planet's size and the other to estimate its mass. With both pieces of information, they could calculate density, which in turn gave clues about composition. Was the planet rocky, like Earth, gassy, like Neptune, or something in between? Other techniques came into play as well. Gravitational microlensing, for example, relies on the way a star's gravity can act like a lens, magnifying the light of a more distant star behind it. If the foreground star has a planet, the planet's gravity can create a brief, additional blip in the light curve. This method is particularly good at finding planets that are far from their stars, even at great distances from Earth. Direct imaging, long thought nearly impossible, also began to make progress. By using advanced optics and clever data processing, astronomers learned how to block out much of a star's light and capture faint images of large young planets orbiting far from their suns. These images do not show much detail, but they provide a direct view of worlds that were once purely theoretical. With each new method, the picture of the galaxy became richer. Planets were found around stars of all kinds, small, cool red dwarfs, sun-like yellow stars, even some larger, hotter stars. Systems were found that looked orderly and systems that looked chaotic. Some had planets locked in neat resonances, their orbits synchronized like gears. Others showed signs of past upheavals, with planets on tilted or elongated paths. What started as a question about whether other worlds existed became a study of how planetary systems evolve and change over time. There was also a subtle shift in the emotional tone of the field. Early on, each discovery was a headline. A new planet was a rare event, something to celebrate. As the numbers grew into the hundreds, then thousands, the focus moved away from individual worlds and toward patterns and statistics. How common are Earth-sized planets? How often do they appear in habitable zones? Do certain types of stars tend to have certain types of planets? These questions require large samples and careful analysis, and they turn the search into something that feels a bit more like a census than an exploration. Yet, even within the statistics, individual worlds still stand out. A planet with a year that lasts just a few hours. A system with 7 rocky worlds packed together. A planet with an atmosphere that seems to contain water vapor. Each one becomes a small story within the larger dataset. The discovery of the first exoplanets also had an impact beyond astronomy. It filtered into culture, into education, into the way people talk about the universe. The idea that there are other worlds out there, potentially like our own, moved from science fiction into everyday conversation. Children grew up knowing that planets around other stars were not just a possibility, but a fact. Writers and artists drew on real discoveries rather than imagined ones. The night sky became, in a sense, more crowded, even though it looked the same to the naked eye. There is something quietly profound about that shift. For thousands of years, humans looked at the stars and saw them as distant, unreachable points of light. Now, when astronomers look at them, they see potential systems with orbits, atmospheres, and maybe even climates. The first discoveries also taught humility. The early assumption that other systems would look like our own turned out to be wrong. Hot Jupiters, super-Earths, tightly packed planetary families, all of these challenged our expectations. Nature, it seemed, was far more creative than our initial models allowed. This creativity is part of what makes the ongoing search so engaging. Every new detection has the potential to add a twist to the story. A planet that does not quite fit the categories. A system that behaves in an unexpected way. A measurement that hints at chemistry we did not anticipate. As instruments continue to improve, the focus has begun to shift again. From finding planets to characterizing them, from counting worlds to trying to understand what they are like. New telescopes are designed to analyze the light that passes through a planet's atmosphere during a transit, looking for the fingerprints of molecules. Others aim to take direct images of Earth-sized planets around nearby stars, separating their faint glow from the overwhelming light of their suns. These efforts build directly on the foundation laid by those first discoveries. Without the confirmation that planets exist around other stars, there would be little reason to invest in such ambitious projects. The initial detections turned a speculative field into a concrete one, where each new tool promises not just more dots on a chart, but more insight into the nature of distant worlds. Looking back, it is striking how recent all of this is. The first confirmed exoplanets were found less than a human lifetime ago. In the span of a few decades, we have gone from 0 known planets beyond our solar system to thousands. This rapid progress suggests that we are still at the beginning of the story. The easiest planets to find have mostly been found. The ones that remain, smaller, cooler, more Earth-like, are more subtle. They require better instruments, longer observations, and more careful analysis. As those worlds come into view, the questions will shift again. Instead of asking how many planets there are, we will ask how many of them have atmospheres. How many show signs of water? How many might have the chemical imbalances that suggest something living is at work? In a sense, the discovery of the first exoplanets opened a door. It did not answer the big questions about life in the universe, but it made those questions feel grounded in reality rather than speculation. Somewhere out there, among the countless stars in the galaxy, are worlds that were once invisible to us. Now, through tiny shifts in light and careful measurements of motion, they have become part of our understanding of the cosmos. When people talk about the habitable zone, it often sounds like a neatly drawn ring around a star, a simple, glowing band where life-friendly worlds line up like houses on a street. In reality, it is less like a sharp boundary, and more like a wide, gradual transition, a region where conditions slowly shift from too cold to too warm, with many shades in between. Thinking about it this way can make the idea feel less like a rule, and more like a quiet suggestion the universe makes to its planets. At the most basic level, the habitable zone is defined by one simple question. Could a planet in this region, if it had the right kind of atmosphere, maintain liquid water on its surface? That is it. No promises about breathable air, gentle weather, or familiar landscapes. Just the possibility that water might stay in that useful in-between state where it can flow, dissolve things, and take part in chemistry. The reason this question matters so much goes back to what we know about life on Earth. Every living thing here, from the smallest bacterium to the largest tree, relies on water in some way. Inside cells, water is the stage where chemical reactions take place. It carries nutrients, helps shape proteins, and allows molecules to meet and interact. So when astronomers look outward, they naturally look for places where water might be able to exist as a liquid, because that is the one proven ingredient they know how to recognize. But even this simple-sounding definition hides a lot of complexity. A planet's ability to hold liquid water does not depend only on how far it is from its star. It depends on the star's brightness, the planet's atmosphere, its reflectivity, its rotation, and even how heat moves around its surface. To understand why, it helps to think about stars themselves. Not all stars shine the same way. our Sun is a fairly average star, moderate in size and brightness, with a steady output of energy that changes only slowly over billions of years. But many stars in the galaxy are much smaller and cooler. Others are larger and far more luminous. A small, cool star, often called a red dwarf, gives off much less energy than the Sun. That means its habitable zone lies much closer in. A planet has to orbit near the star to receive enough warmth for water to stay liquid. On the other hand, a large bright star pours out enormous amounts of energy, so its habitable zone sits far away, sometimes at distances greater than the orbit of Mars in our own solar system. This shift in the location of the habitable zone has consequences for the planets that might live there. Around a red dwarf, a potentially habitable planet might be so close to its star that its year lasts only a few days or weeks. Around a larger star, a similar planet might take years or even decades to complete a single orbit. Closeness to a star can also lead to something called tidal locking. This happens when a planet's rotation slows down until one side always faces the star, much like the Moon always shows the same face to Earth. In this situation, one hemisphere is in constant daylight, while the other remains in perpetual night. At first, this might sound like a recipe for disaster. The day side could become extremely hot, while the night side could freeze. But atmospheres can change this picture. If a planet has a thick enough atmosphere, winds can carry heat from the warm side to the cool side, smoothing out the temperature differences. Some models suggest that a tidally locked planet could still have a broad region around the line between day and night, a kind of endless twilight zone where conditions might be relatively moderate. So even within the habitable zone, the actual experience on the surface of a planet can vary widely. Two planets at the same distance from their star could have very different climates depending on their atmospheres, their rotation rates, and how their surfaces reflect or absorb light. Reflectivity, often called albedo, plays a quiet but important role. A bright, icy surface reflects much of the incoming starlight back into space, keeping the planet cooler. A dark, ocean-covered surface absorbs more light, warming the planet. This means that a world near the inner edge of the habitable zone could stay comfortable if it reflects a lot of light, while a world near the outer edge might remain warm if it absorbs more. Earth itself demonstrates this balance. Our planet reflects about 30% of the sunlight that hits it, thanks to clouds, ice, and bright land surfaces. If that number were much higher or lower, our climate could be very different. Then there is the atmosphere's greenhouse effect. Certain gases, like carbon dioxide, methane, and water vapor, trap heat. They let sunlight in, but slow the escape of infrared radiation back into space. The amount and type of these gases can dramatically change a planet's surface temperature. This is why the habitable zone is sometimes described as conservative or optimistic, depending on how much greenhouse warming you assume. A planet with a thick heat-trapping atmosphere might be able to maintain liquid water, even if it orbits slightly outside the traditional outer edge of the zone. A planet with a thin atmosphere might need to be closer in. As astronomers refine their models, they often talk about different versions of the habitable zone. The inner edge might be defined by the point where a planet would experience a runaway greenhouse effect, like Venus, where increasing temperatures cause more water vapor to enter the atmosphere, which traps more heat, which raises temperatures further in a self-reinforcing loop. The outer edge might be defined by the point where even a thick atmosphere full of carbon dioxide cannot keep the surface warm enough to prevent global freezing. Between those edges lies a wide range of possibilities, and within that range there are countless variations in climate, weather, and surface conditions. It is also worth remembering that stars change over time. Our Sun was dimmer in its youth and has slowly grown brighter as it ages. That means the habitable zone has moved outward over billions of years. Early in Earth's history, our planet received less sunlight than it does now, yet there is evidence that liquid water still existed on the surface. This suggests that Earth's atmosphere and other factors compensated for the lower energy output of the young Sun. This idea, sometimes called the faint young sun paradox, highlights how a planet's internal and atmospheric processes can extend or shift its window of habitability. A world might start out too cold, then become comfortable as its star brightens. Or it might start comfortable and become too hot as its star ages. For stars much larger than the Sun, this process happens faster. These stars burn through their fuel quickly, changing significantly over hundreds of millions of years rather than billions. That can make their habitable zones short-lived in cosmic terms. A planet might only have a brief window where conditions are right for liquid water before the star becomes too bright or evolves into a different phase. On the other hand, red dwarfs can live for trillions of years, far longer than the current age of the universe. Their habitable zones may be narrow and close in, but they can remain stable for unimaginably long periods of time. If a planet around a red dwarf can hold on to its atmosphere and survive the star's active youth, it might have a very long stretch of relative calm in which life could develop. This trade-off between stability and harsh beginnings is one of the central questions in the study of habitability around different types of stars. Red dwarfs are common, making up the majority of stars in the galaxy. That alone makes them attractive targets, but they're also known for producing strong flares, especially when they're young. These bursts of radiation could strip atmospheres or damage surface chemistry. Some models suggest that planets might recover from this early violence, rebuilding their atmospheres through volcanic activity or the release of gases from the interior. Others suggest that many of these worlds might be left bare and dry. The truth likely varies from system to system. Another layer of complexity comes from planetary orbits themselves. Not all orbits are nice and circular. Some planets follow elongated, elliptical paths that take them closer to their star at one point and farther away at another. This can lead to significant temperature swings over the course of a year. A planet might spend part of its orbit within the habitable zone and part of it outside. Whether that world could maintain stable conditions depends on how quickly it heats up and cools down, how much heat its oceans or atmosphere can store, and how extreme the variations are. In some cases, these variations might create a climate with strong seasons, far more dramatic than what we experience on Earth. In others, the planet's systems might smooth things out enough that liquid water remains present somewhere on the surface throughout the orbit. The idea of somewhere on the surface is important. Even on Earth, not every region is equally hospitable. There are deserts, polar ice caps, deep oceans, and high mountain ranges. Life has found ways to exist in all of these, but in very different forms. So when astronomers say a planet is in the habitable zone, they are not implying that the entire surface is a global garden. They are suggesting that, under the right conditions, there could be regions where water is liquid and chemistry can proceed in interesting ways. This perspective also opens the door to the idea of partial habitability. A world might be mostly frozen, with a narrow equatorial band of open water, or it might be mostly dry, with isolated lakes or seas, or it might have a thick atmosphere that creates high pressures, changing how water behaves at the surface. As our understanding grows, the habitable zone becomes less of a simple label and more of a starting point for deeper questions. What kind of atmosphere does the planet have? How does heat move around its surface? What is its geological history? Does it have oceans, continents, ice caps, or something else entirely? There is also a growing interest in what some scientists call the galactic habitable zone. This idea zooms out even further, looking at where in a galaxy conditions might be most favourable for life. Near the centre of a galaxy, stars are packed closely together, and supernovae and radiation levels can be high. Farther out, there may be fewer heavy elements needed to build rocky planets. Our own solar system sits in a region that seems to strike a balance, with enough heavy elements to form planets like Earth, and enough distance from the crowded energetic core to avoid frequent catastrophic events. This adds another layer to the story of habitability, one that connects individual worlds to the broader structure of the galaxy. Even within a single system, the presence of other planets can influence the habitable zone. Large gas giants can shape the orbits of smaller worlds, sometimes stabilizing them, sometimes making them more chaotic. They can also affect the delivery of water and other materials during the early stages of planet formation by redirecting icy bodies from the outer system toward the inner planets. In this way, a planet's potential to be habitable is tied not just to its star, but to its planetary neighbours and the history of the entire system. When astronomers search for habitable zone planets, they often start with the easiest cases: stars that are quiet and stable, planets that orbit at distances where transits are likely to be observed, systems that are close enough to Earth for detailed follow-up observations. As technology improves, the search expands. Smaller stars, fainter stars, more distant stars all come into view. With each new detection, the habitable zone becomes populated with more examples, each one slightly different from the last. Some of these worlds challenge our expectations. There are planets that appear to be larger than Earth but still rocky, sometimes called super-Earths. Their stronger gravity could hold on to thicker atmospheres, which might extend the range of the habitable zone for those worlds. But that same thick atmosphere could also create high pressures and temperatures at the surface. There are also planets that might be entirely covered in deep oceans with no land at all. These ocean worlds could exist within the habitable zone, but their chemistry and climate would be very different from Earth's. Without exposed land, processes like weathering and carbon cycling would work in unfamiliar ways. As these possibilities pile up, the habitable zone starts to feel less like a single, glowing ring and more like a wide, layered region of potential, a place where many different kinds of worlds might exist, each with its own version of what it means to be warm enough, wet enough, and stable enough. It is also important to remember that the habitable zone is defined in terms of surface conditions. But as we discussed earlier, some of the most promising places for life in our own solar system might be beneath the surface, in hidden oceans warmed by internal heat. These worlds fall outside the traditional habitable zone, yet they may still be alive with chemistry and energy. This raises the possibility that our focus on the habitable zone, while useful, might be only part of the picture. There could be many more life-friendly environments scattered throughout planetary systems, tucked away beneath ice or rock, invisible to our current methods. Still, the habitable zone remains a powerful concept because it gives astronomers a place to start, a way to narrow down the vast number of planets in the galaxy to a smaller set of worlds that might be worth closer examination. When you think about it in that way, the gentle glow of the habitable zone around distant stars is less about a precise boundary and more about an invitation to look more closely, to ask more detailed questions, to imagine what conditions might be like on worlds we can barely detect. Every potentially habitable planet we find adds another point of light to this picture, not a literal light we can see in the sky, but a data point in our growing map of where life might be possible. When we shift our attention from the planets themselves to the stars they orbit, the whole idea of habitability starts to feel less like a question about places and more like a question about relationships. A planet, no matter how well built or well positioned, is shaped over time by the light, heat, and energy of its star. In a very real sense, every potentially habitable world is a reflection of the kind of sun it circles, and understanding those suns is a way of understanding the long-term prospects of the worlds that depend on them. It can be tempting to think of stars as mostly the same, just brighter or dimmer points in the sky. But in reality, stars come in a wide range of sizes, temperatures, lifespans, and personalities. Some are steady and predictable, shining quietly for billions of years. Others are restless, flaring and pulsing, changing their output in ways that can make life on nearby planets a much more complicated affair. Astronomers classify stars into different types based on their temperature and the light they emit. This system, often remembered by the slightly whimsical sequence OBAFGKM, runs from the hottest, brightest stars to the coolest, dimmest ones. Our Sun is a G-type star, sitting comfortably in the middle of this range. Red dwarfs, the small, cool stars that make up the majority of stars in the galaxy, fall into the M-type category at the cooler end. Each of these types creates a very different environment for the planets that orbit them. Let's start with the stars most familiar to us, the quiet, steady ones like our Sun. G-type stars are not the most common in the galaxy, but they are not rare either. They burn hydrogen in their cores at a moderate rate, producing a stable output of energy that changes only slowly over time. Our Sun has been shining for about 4.6 billion years, and it is expected to continue doing so for several billion more before it begins to change more dramatically. This long, stable period is one of the reasons Earth has had so much time to develop complex life. The Sun's brightness has increased gradually, giving Earth's climate and biological systems time to adapt. There have been ups and downs, ice ages and warm periods, but the overall energy input from the Sun has stayed within a range that allowed liquid water to persist on the surface for most of the planet's history. For planets orbiting stars like this, the habitable zone tends to be at a comfortable distance, far enough out that tidal locking is unlikely. That means these planets can rotate freely, creating day and night cycles that distribute heat more evenly around the globe. This kind of rhythm is something we are very familiar with, and it is easy to imagine life adapting to it. But stars like the Sun are not the only candidates for hosting potentially habitable worlds. In fact, they are outnumbered by smaller, cooler stars that dominate the galaxy. Red dwarfs are the most common type of star in the Milky Way. They are small, sometimes only a tenth the mass of the Sun, and they shine with a faint reddish light. Because they burn their fuel very slowly, they can live for an extraordinarily long time. Some estimates suggest that the smallest red dwarfs could shine for trillions of years, far longer than the current age of the universe. This incredible longevity makes them intriguing targets in the search for life. If a planet around a red dwarf can maintain habitable conditions, it could have an enormous window of time for life to develop, evolve, and diversify. At the same time, red dwarfs come with challenges of their own. Because they are so dim, their habitable zones lie very close in. A planet needs to orbit near the star to receive enough warmth for liquid water. This closeness increases the likelihood of tidal locking, where one side of the planet always faces the star. As we've mentioned before, this creates a world with a permanent day side and a permanent night side. The star-facing side might be bathed in constant light and heat, while the far side remains in darkness and cold. Between them lies a narrow region of twilight. Whether such a world could be comfortable enough for life depends on its atmosphere and oceans. If heat can be transported efficiently from the day side to the night side, the temperature differences might be softened. Winds, currents, and clouds could play a role in spreading energy around the planet. Some climate models suggest that a thick atmosphere could create a relatively stable environment, even on a tidally locked world. Others point out that the same atmosphere might also be vulnerable to being stripped away by the star's activity. This brings us to one of the defining traits of red dwarfs, especially when they are young. They are often very active. Many produce frequent and powerful flares, bursts of radiation, that can dramatically increase the amount of high-energy particles and ultraviolet light hitting nearby planets. For a planet orbiting close to such a star, these flares can be a serious problem. Over time, they can erode the planet's atmosphere, breaking molecules apart and allowing lighter gases to escape into space. They can also bathe the surface in radiation that would be harmful to many forms of life as we know it. That does not necessarily mean life is impossible in these environments. It might mean that life would need to find shelter, perhaps underground or underwater, where it is shielded from radiation. It might also mean that only certain kinds of planets, those with strong magnetic fields or very thick atmospheres, can hold on to their protective layers over long periods of time. The early history of a red dwarf system is particularly important. Many of these stars go through a very active phase when they are young, emitting strong flares and intense radiation. If a planet can survive this period with its atmosphere mostly intact, It might then enjoy a very long, calm adulthood around a star that changes only slowly over trillions of years. In this way, red dwarf systems can be seen as high-risk, high-reward environments for habitability. The beginnings may be harsh, but the potential long-term stability is unmatched. Moving up the scale in size and brightness, we come to K-type stars, sometimes called orange dwarfs. These stars are a bit smaller and cooler than the Sun, but not as dim as red dwarfs. They are less common than red dwarfs, but still quite abundant. K-type stars often strike a balance that makes them particularly interesting to astronomers searching for potentially habitable planets. Their habitable zones are closer in than the Sun's, but not so close that tidal locking is guaranteed. They tend to be less active and flare-prone than many red dwarfs, offering a calmer environment for nearby planets. They also live longer than G-type stars like the Sun, though not as long as the smallest red dwarfs. This gives planets around them a long, stable window for life to develop, without some of the more extreme challenges posed by very small stars. Some scientists have suggested that K-type stars might represent a kind of sweet spot in the search for life, combining longevity with relative calm. They are bright enough to support photosynthesis as we understand it, but not so energetic that they pose constant threats to planetary atmospheres. Then there are the stars larger and brighter than the Sun, such as F-type stars and beyond. These stars shine intensely, pouring out more energy and light. Their habitable zones are located farther away, which can reduce some of the issues associated with close-in orbits, like tidal locking. However, these stars burn through their fuel much more quickly. An F-type star might only remain stable for a few billion years, or even less. That might sound like a long time, but in terms of biological evolution, it could be a tight schedule. On Earth, it took billions of years for complex life to emerge. If a planet around a larger star has only a relatively short window of stable conditions before the star changes dramatically, that might limit how far life can develop. As stars like this age, they tend to grow brighter and eventually expand into red giants, altering or destroying the habitable zones of their systems. A planet that starts out in a comfortable region might find itself slowly overheating as the star evolves. So while larger, brighter stars can host habitable zones, the long-term prospects for life around them may be more limited. All of this means that when astronomers look at a potentially habitable planet, one of the first things they want to know is the type of star it orbits. That single piece of information can hint at the planet's past, present and future in profound ways. Beyond size and temperature, there is also the question of stellar stability. Some stars vary in brightness over time, either in regular cycles or more chaotic patterns. These changes can affect the climates of their planets. Our own Sun goes through an approximately 11-year cycle of activity, marked by changes in the number of sunspots and the frequency of solar flares. This cycle has subtle effects on Earth's upper atmosphere and space environment, but it does not drastically alter the climate. Other stars can be much more variable. Some pulsate, growing brighter and dimmer in regular rhythms. Others experience large, unpredictable changes. A planet orbiting such a star would have to cope with shifting energy input, which could lead to dramatic climate variations. Another layer of complexity comes from the spectrum of light a star emits. Not all starlight is the same. Red dwarfs emit more of their energy in the infrared, while larger, hotter stars emit more in the ultraviolet and visible range. This matters for things like photosynthesis. On Earth, plants and other photosynthetic organisms use visible light to power the chemical reactions that produce energy. On a planet orbiting a red dwarf, the available light might be more heavily weighted toward infrared. Could life evolve a different kind of photosynthesis that uses this lower energy light? Some scientists think it might be possible. After all, even on Earth, there are organisms that use different pigments to capture different parts of the light spectrum. The colour of a star could also affect how a planet's sky and surface appear. A world under a red dwarf might have a sky that looks darker, even at midday, because the star's light is dimmer to our eyes. The plants, if any exist, might not be green, but some other colour that reflects the kind of light available. These are small details in the grand scheme, but they highlight how deeply a planet's environment is tied to its star. There is also the matter of how stars and planets form together. The composition of a star, especially the amount of heavier elements it contains, can influence the kinds of planets that form around it. Astronomers often use the term metallicity to describe the abundance of elements heavier than hydrogen and helium in a star. Stars with higher metallicity tend to have more material available in their surrounding disks to form planets, especially rocky ones. This means that regions of the galaxy that are richer in heavy elements might be more likely to host Earth-like worlds. Our Sun is relatively rich in these elements, which is one of the reasons our solar system contains a variety of rocky planets, gas giants, and smaller bodies. When astronomers study other stars, they often measure their metallicity to get a sense of what kinds of planetary systems they might have. The neighbourhood a star lives in also matters. In dense star clusters, stars are packed closely together. Close encounters between stars can disrupt planetary orbits, potentially ejecting planets from their systems or sending them into unstable paths. Regions with high rates of supernovae can be bathed in radiation that affects nearby systems. Our solar system resides in a relatively quiet part of the galaxy, far from the crowded centre and not particularly close to any massive short-lived stars. This calm environment may have helped maintain the stability needed for life to develop over long periods. When astronomers look for stars that might host habitable planets, they often consider these broader galactic factors as well. It is not just about the star itself, but about the company it keeps and the region of the galaxy it inhabits. As surveys continue and catalogues of exoplanets grow, patterns begin to emerge. Certain types of stars seem more likely to host certain types of planets. Hot Jupiters, for example, are more commonly found around stars with higher metallicity. Smaller rocky planets appear to be common around a wide range of stars, including red dwarfs. This statistical approach helps refine the search. Instead of looking everywhere equally, astronomers can focus on stars that, based on what we have learned so far, are more likely to host worlds of interest. At the same time, there is a sense of openness in the field. Nature has already surprised us many times. Hot Jupiters were unexpected. Super-Earths, a class of planets that does not exist in our own system, turned out to be common. Tightly packed systems challenged our ideas about how planets move and settle into stable orbits. It would not be surprising if the relationship between stars and habitability holds a few more surprises as we look more closely. In the end, thinking about red dwarfs, quiet suns, and all the other stars that light up the galaxy is a way of stepping back and seeing the broader context of our search. Planets do not exist in isolation. They are part of systems, and those systems are shaped by the stars at their centres. Every potentially habitable world we find carries with it the imprint of its sun. The colour of its sky, the rhythm of its days, the stability of its climate and the fate of its atmosphere are all tied to the nature of the star it orbits. When astronomers first began to realise just how many planets might be scattered throughout the galaxy, the idea of a system with not one, not two, but several potentially habitable worlds orbiting a single star still felt like a distant, almost speculative dream. It was one thing to find a lone planet in the right place around a distant sun. It was another to imagine a whole family of worlds, clustered together, each following its own path, each shaped by the same faint, steady glow of a single small star. Then, quietly and without much fanfare at first, the TRAPPIST-1 system entered the story and changed the tone of that imagination. TRAPPIST-1 is not a star you can see with your eyes. It is small, cool, and dim, located about 40 light-years away in the constellation Aquarius. Compared to our Sun, it is tiny, only about 9% as massive and far less luminous. It shines with a soft reddish light, the kind of glow that would make even a clear day on a nearby planet feel more like a deep twilight than a bright afternoon. Yet around this faint star, astronomers discovered something remarkable. Not just a single planet, but 7. 7 rocky worlds, all orbiting closer to their star than Mercury does to the Sun, packed into a region of space so compact that, if you placed them in our own solar system, they would all fit comfortably within the orbit of our innermost planet. The discovery unfolded in stages. In 2016, astronomers using a small ground-based telescope in Chile, part of a project called TRAPPIST, announced the detection of 3 planets around this star. The name TRAPPIST itself is an acronym for the telescope project, but it also happens to evoke the idea of something carefully crafted and quietly refined, which feels fitting for a system that would soon capture so much attention. The following year, using data from NASA's Spitzer Space Telescope and other observatories, the same team revealed that the system actually contained 7 planets. All 7 appeared to be roughly Earth-sized, or at least within the range that suggested they were rocky rather than gaseous. Even more intriguing, 3 of them were located in the star's habitable zone, where temperatures could allow liquid water to exist on their surfaces. For the first time, astronomers had a system where multiple, potentially habitable worlds existed side by side orbiting the same star. It was not just a single dot on a chart, it was a cluster of possibilities. To understand why this system is so special, it helps to picture the layout. The planets are named TRAPPIST-1b through H, starting from the one closest to the star and moving outward. Their orbits are incredibly tight. The innermost planet completes a full trip around the star in just about 1.5 Earth days. The outermost one takes about 18.8 days. This means that if you were standing on one of these planets, the passage of time would feel very different from what we're used to. A year would last only a couple of weeks, at most. The star would rise and set, or perhaps hang in the same place in the sky if the planet were tidally locked, at a pace that would make our own calendar feel slow and sprawling by comparison. The closeness of the planets to each other is also striking. In some cases, the distance between neighbouring worlds is only a few times the distance between Earth and the Moon. That means that from the surface of one planet, the others would appear large and bright in the sky, sometimes larger than our Moon appears to us. Imagine looking up at night, or during a long, dim twilight, and seeing another world hanging overhead, a disk with visible shading, perhaps even hints of surface features if the atmosphere were clear enough. On some of these planets, you might be able to see the neighbouring worlds go through phases, growing and shrinking in the sky, much like the Moon does for us. This visual closeness is not just a poetic detail. It hints at how interconnected the system is in a gravitational sense. The planets tug on each other as they orbit, creating a kind of rhythmic dance. Their orbits are locked into a pattern called a resonance, where the timing of each planet's orbit is related to the others in a precise mathematical way. For example, every time one planet completes a certain number of orbits, another completes a different but related number. This keeps the system stable over long periods of time, preventing the planets from drifting into chaotic paths that might lead to collisions or ejections. This kind of resonance also allows astronomers to measure the planets' masses with surprising precision. By tracking the slight variations in the timing of each transit, caused by the gravitational pulls between the planets, scientists can estimate how heavy each world is. Combined with measurements of their sizes, this gives clues about their densities and, by extension, their compositions. The results suggest that all 7 planets are likely rocky, or at least have solid surfaces, rather than being wrapped in thick envelopes of gas like Neptune or Jupiter. Some may have significant amounts of water, either on the surface or locked up as ice. The 3 planets in the habitable zone, TRAPPIST-1, E, F and G, are especially interesting. Based on current models, TRAPPIST-1e is often considered the most Earth-like of the group. It receives a similar amount of energy from its star as Earth does from the Sun, though that energy is delivered in a very different form, skewed toward infrared light. This planet is also thought to have a density consistent with a rocky composition, and possibly a substantial amount of water. That does not mean it has oceans and continents like Earth, but it does suggest that it could be a world where liquid water might exist somewhere on or near the surface. TRAPPIST-1F and G receive slightly less energy, placing them toward the cooler side of the habitable zone. They might be colder, perhaps with large areas of ice, but still within the range where liquid water could exist under the right atmospheric conditions. Of course, all of this depends heavily on the planet's atmospheres, which remain largely mysterious. This star they orbit is a red dwarf, and as we discussed earlier, these stars can be quite active, especially in their youth. TRAPPIST-1 has been observed to produce flares, bursts of radiation that could affect the atmospheres of nearby planets. Because the planets are so close to the star, they are likely tidally locked. This means one side of each planet probably always faces the star, while the other side remains in darkness. The day side would be bathed in constant dim light, and the night side would be in perpetual night. This configuration creates a unique climate challenge. Without a day-night cycle to distribute heat, temperatures could vary dramatically between the two hemispheres. But again, atmospheres can play a role. If the planets have thick enough atmospheres, winds could transport heat from the day side to the night side, creating a more moderate global climate. Some models even suggest that a tidally locked planet could have a stable, ring-shaped region around the line between day and night, where temperatures and lighting conditions are relatively gentle. This so-called terminator zone could, in theory, be a place where liquid water is more likely to persist. In the TRAPPIST-1 system, this idea becomes especially intriguing because of the number of potentially habitable worlds. Each one could have its own version of this twilight region, its own balance between heat and cold, light and dark. The star itself adds another layer of character to the system. TRAPPIST-1 is very small and cool, emitting most of its energy in the infrared. To a human eye, the star would look much dimmer than the Sun, even if it were directly overhead. The sky on these planets might appear darker, with a reddish tint to the light. If there were plants or other photosynthetic organisms on these worlds, they might not be green. They could be darker, perhaps even black, designed to absorb as much of the available light as possible. This is, of course, speculation, but it shows how different the visual experience of such a world could be, even if the basic physics of life were similar. The infrared-rich light from the star also affects how heat is absorbed by the planet's surfaces and atmospheres. Water vapor and carbon dioxide, for example, absorb infrared radiation very effectively. This could enhance the greenhouse effect, potentially helping planets on the cooler side of the habitable zone stay warm enough for liquid water. At the same time, the star's flares and high-energy radiation could pose risks. Over long periods, they might strip away lighter gases from the planet's atmospheres, especially if the planets lack strong magnetic fields to deflect charged particles. Whether TRAPPIST-1's planets can hold onto their atmospheres is one of the big open questions. Some models suggest that if the planets formed with thick atmospheres, they might still have substantial amounts of gas left today. Others suggest that the star's early activity could have removed much of their original air, leaving behind thinner atmospheres or even bare surfaces. Observations are beginning to offer some clues. Using space telescopes, astronomers have started to look at how the planet's atmospheres, if they exist, filter the star's light during transits. For some of the planets, especially the innermost ones, the data suggests that they probably do not have thick hydrogen-rich atmospheres. That does not rule out thinner, more Earth-like atmospheres, but it does narrow down the possibilities. What makes TRAPPIST-1 especially valuable is not just the number of planets, but how accessible the system is for study. Because the star is small, the relative size of the planets compared to the star is large. This means that when a planet passes in front of the star, it blocks a relatively significant fraction of the light, making the transit easier to detect and analyze. This makes the system a prime target for powerful telescopes like the James Webb Space Telescope. With its ability to study infrared light in detail, Webb can look for the chemical signatures of molecules like water vapor carbon dioxide and methane in the planet's atmospheres. Each observation is a slow, careful process. The signals are faint and the interpretations are cautious. But over time, they promise to turn these distant points of data into something more like real places, with temperatures, pressures, and compositions that we can begin to imagine. There is also a broader, almost philosophical impact to a system like TRAPPIST-1. It challenges the idea that habitable worlds are isolated, rare gems scattered thinly across the galaxy. Here is a single star with multiple rocky planets, several of which might be capable of supporting liquid water. If systems like this are common, it suggests that the galaxy could be full of clusters of potentially habitable worlds, rather than just lone Earth-like planets here and there. At the same time, the uniqueness of the system reminds us not to generalize too quickly. TRAPPIST-1 is an extreme case in many ways. Its planets are unusually tightly packed. Its star is unusually small and cool. The conditions there are likely very different from those in systems around stars like our Sun. Still, the system serves as a kind of natural laboratory. It allows scientists to test their models of planetary formation, orbital dynamics, atmospheric evolution, and climate under conditions that are very different from those in our own solar system. For example, how did 7 rocky planets end up so close together? Did they form in place, or did they migrate inward from farther out? How did they acquire their water, if they have any? Were icy bodies from the outer system redirected inward, delivering water during the early stages of formation? These questions tie the TRAPPIST-1 system into the larger story of how planetary systems form and evolve. The answers could help us understand not just this one star, but the broader population of systems throughout the galaxy. From a more personal perspective, it is hard not to be drawn to the image of a sky filled with neighbouring worlds. The idea that, on some distant planet, the night sky might be dominated by the presence of other planets, rather than just tiny points of light, feels both strange and strangely familiar. It invites you to imagine what it would be like to grow up on such a world, to have another planet as a constant companion in the sky, to mark time by its phases and movements. Of course, all of this remains firmly in the realm of imagination for now. We have not seen the surfaces of these planets. We do not know if they have oceans, continents, clouds, or skies in the way we picture them. We do not know if they're quiet, barren rocks or places where chemistry is busily at work. What we do know is that the TRAPPIST-1 system has given us one of the most detailed and intriguing examples of a multi-planet system with potentially habitable worlds. It has turned an abstract concept into a concrete target for observation and study. As we continue to look at this system, it will likely continue to surprise us. New data may reveal thick atmospheres, thin ones, or something in between. It may show signs of water, or it may suggest that these worlds are drier than we hoped. Either way, the system stands as a reminder that the galaxy is capable of producing arrangements of worlds that are both orderly and exotic, simple in their underlying physics and complex in their outcomes. Far beyond the familiar constellations that map our night sky, in a patch of space that looks no different from any other to the naked eye, a small, unassuming spacecraft once stared, without blinking for years on end. It did not chase comets or swing past planets. It did not take sweeping photographs of galaxies. Instead, it fixed its gaze on a single field of stars and waited patiently for the faintest hints of movement and shadow. That quiet, stubborn focus is what turned the Kepler Space Telescope into one of the most influential planet hunters in human history, and what transformed our sense of how many Earth-like worlds might be scattered through the galaxy. Kepler's mission began in 2009 with a simple but ambitious goal. It was designed to answer a question that had lingered for generations, whispered in science fiction, and debated in scientific papers. How common are planets like Earth? Not just planets in general, but small, rocky worlds that orbit their stars at distances where liquid water might exist. Before Kepler, astronomers had found a handful of such candidates. but the sample was too small to draw meaningful conclusions. The galaxy could be full of them, or they could be exceedingly rare. There was no way to know. To solve this, Kepler did something bold. Rather than surveying the entire sky, it picked a single region and watched it continuously. Its field of view contained over 150,000 stars, each one a potential host for unseen planets. The idea was not to find every planet in the galaxy, but to find enough in one well-defined sample to make reliable estimates about the whole. The method Kepler used, the transit technique, relies on alignment and timing. If a planet's orbit happens to line up with our line of sight, it will pass in front of its star once every orbit. Each time it does, it blocks a tiny fraction of the star's light. For a gas giant, this dip is relatively easy to spot. For an Earth-sized planet, the change is minuscule, often less than 0.01%. Detecting such a small signal requires extraordinary precision and stability. Kepler was built for exactly this task. It carried a sensitive photometer and a large, steady mirror, and it was placed in an orbit around the Sun that allowed it to maintain a fixed orientation toward its chosen patch of sky. This meant it could monitor the brightness of each star with remarkable consistency over long periods. As the data began to flow back to Earth, patterns emerged. Some stars dimmed regularly like a heartbeat. Others showed occasional, irregular dips. Each potential transit had to be examined carefully. Not every dip in brightness is caused by a planet. Star spots, binary stars, and instrumental noise can all create false signals, so each candidate went through layers of analysis and follow-up observations. Even with this careful approach, the number of potential planets grew quickly. Within the first few years, Kepler had identified thousands of candidates. The sheer volume of discoveries was staggering. What had once been a trickle of new worlds became a steady stream. Among this flood of data, a particularly exciting category began to take shape. These were the small planets, roughly the size of Earth or slightly larger, orbiting in or near the habitable zones of their stars. Each one was a quiet suggestion that our own planet might not be a lonely exception. One of the early highlights was Kepler 186f. This planet, discovered in 2014, was the first confirmed Earth-sized planet found in the habitable zone of another star. It orbits a red dwarf about 500 light-years away. Its size is very close to Earth's, and it receives about a third of the energy from its star that Earth gets from the Sun. This places it on the cooler side of the habitable zone. If it has an atmosphere, especially one with greenhouse gases, it could potentially maintain liquid water on its surface. Without such an atmosphere, it might be a frozen world. Either way, its discovery was a milestone. It showed that Earth-sized planets in habitable zones were not just theoretical possibilities, they existed. Then came Kepler 452b, sometimes described as Earth's older cousin. This planet orbits a star similar to the Sun, though slightly older and brighter. Kepler 452b is larger than Earth, about 60% wider in diameter, placing it in the category of a super-Earth. It sits in the habitable zone of its star, receiving a similar amount of energy as Earth does. The age of the system added another layer of interest. If life takes a long time to develop, as it did on Earth, then an older system might have had more time for complexity to arise. Of course, this is speculative, but it highlights how Kepler's discoveries allowed astronomers to start thinking not just about where planets are, but about how long they have been there under potentially stable conditions. As more candidates were analysed, it became clear that Earth-sized planets were not rare. In fact, they seemed to be quite common, especially around smaller stars. This led to a shift in how scientists estimated the number of potentially habitable worlds in the galaxy. Using Kepler's data, astronomers began to calculate a value often referred to as eta-Earth. This represents the fraction of stars that have at least one Earth-sized planet in the habitable zone. Early estimates varied widely, but as the data improved, a general picture emerged. Depending on the type of star, Anywhere from a few percent to a few tens of percent might host such a planet. Given that the Milky Way contains hundreds of billions of stars, even the lower end of those estimates suggests that there could be billions of potentially habitable planets in our galaxy alone. This realization had a subtle but powerful effect on the conversation about life in the universe. It shifted the question from "are there any other Earth-like planets?" to "how many are there, and how close might the nearest one be?" Kepler's treasure chest was not limited to planets that neatly fit our expectations. Many of its most interesting discoveries were worlds that did not have clear analogues in our own solar system. One such category is the super-Earth. These are planets larger than Earth but smaller than Neptune. Some may be rocky, with thick atmospheres. Others might have deep layers of water or ice beneath dense clouds of gas. Their gravity is stronger than Earth's, which could affect everything from the height of mountains to the behaviour of atmospheres and oceans. Kepler found that super-Earths are common. In fact, they appear to be one of the most prevalent types of planets in the galaxy. This was surprising, because our own solar system does not contain any. We have small rocky planets and large gas giants, but nothing in between. This discovery suggested that our system might be somewhat unusual, or at least not representative of the most common planetary arrangements. It also meant that many potentially habitable worlds might not look like scaled copies of Earth. They could be heavier, with denser atmospheres and different surface conditions. Another unexpected find was the prevalence of tightly packed planetary systems. Kepler uncovered many stars with multiple planets orbiting very close together, often with periods of just a few days or weeks. These systems challenge our models of how planets form and migrate. In some cases, the planets in these systems are locked into resonant patterns, similar to what we see in TRAPPIST-1. In others, they appear to be in more loosely organised arrangements. Each system provides another test case for theories of planetary dynamics. Kepler also revealed that planets come in a wide range of densities. By combining transit data with measurements of stellar wobble from ground-based telescopes, astronomers could estimate both the size and the mass of some planets. This allowed them to calculate density, which gives clues about composition. Some Earth-sized planets turned out to be surprisingly dense, suggesting they're rich in iron and other heavy elements. Others were less dense, hinting at thick atmospheres or large amounts of water. This diversity suggests that even among planets of similar size, the internal and surface conditions can vary widely. As the catalogue grew, astronomers began to look for patterns in where different types of planets tend to form. They found, for example, that small rocky planets are common around red dwarfs and sun-like stars alike. Gas giants, on the other hand, seem to be more common around stars with higher metallicity, meaning stars that formed from material rich in heavy elements. These patterns help refine the search for potentially habitable worlds. If certain types of stars are more likely to host rocky planets in their habitable zones, those stars become prime targets for future observations. One of Kepler's most valuable contributions was not a single discovery, but a statistical foundation. By knowing how many stars it observed and how many planets it detected, astronomers could correct for the fact that only a fraction of planetary systems are aligned in such a way that transits are visible from Earth. This correction allowed them to estimate the true number of planets out there, not just the ones we happen to see. It is a bit like counting how many people in a crowd are wearing hats, knowing that you can only see the ones standing in front, and then estimating how many more are hidden behind them. Through this process, Kepler turned the galaxy into something like a map of probabilities. It did not show where every planet is, but it revealed how common different types of planets are likely to be. The mission itself faced challenges along the way. In 2013, Kepler lost 2 of its 4 reaction wheels, which it used to maintain its precise pointing. This effectively ended its original mission. But rather than giving up, engineers devised a clever solution that allowed Kepler to continue observing in a modified mode, known as the K2 mission. In this new phase, Kepler observed different fields along the plane of the solar system, expanding its survey to include stars in a variety of galactic environments. This added even more diversity to its catalogue and allowed astronomers to study planetary systems in different contexts. The data from Kepler continues to be analysed years after the spacecraft itself stopped collecting new observations. Scientists and citizen scientists alike have pored over its light curves, looking for overlooked signals and refining the properties of known planets. This ongoing work means that Kepler's treasure chest is not a static collection. It is a living archive, one that continues to yield new insights as methods improve and new questions are asked. There is also a human side to this story. Kepler's discoveries were made public through a steady stream of announcements, each one adding another piece to the puzzle. For people following along, it felt like watching a map of the galaxy slowly fill in with new worlds. The names of the planets, often technical and numerical, did not always capture the imagination in the way that more poetic names might, but the sheer number of them created its own kind of wonder. Kepler 62f, Kepler or 42b, Kepler 1649c. Each one a small, distant world, identified by a faint dip in a star's light. Kepler 1649c, for example, is an Earth-sized planet orbiting a red dwarf about 300 light-years away. It receives a similar amount of energy from its star as Earth does from the Sun, making it one of the most Earth-like candidates in terms of size and insolation. It was initially misclassified and later identified through a reanalysis of the data, showing that even years later, Kepler's observations can still reveal new gems. These kinds of discoveries highlight how much information is packed into those long, steady records of starlight. Each data set is like a quiet diary of a star's behaviour, with the subtle signatures of orbiting worlds hidden in the margins. As we look at Kepler's legacy, it becomes clear that its greatest contribution may be a change in perspective. Before Kepler, Earth-like planets were a topic of speculation and debate. After Kepler, they became a statistical reality. We now know that small rocky planets are common. We know that many stars have systems of multiple planets. We know that a significant fraction of stars likely host planets in their habitable zones. This does not mean that life is common. That is a separate and much harder question. But it does mean that the basic settings for life, at least as we understand it, are not rare. In practical terms, Kepler also helped guide the design of future missions. Knowing that Earth-sized planets are out there gives purpose to telescopes built to study atmospheres and surface conditions. It provides a list of targets, a set of worlds to look at more closely. The Transiting Exoplanets Survey Satellite, or TESS, followed in Kepler's footsteps, scanning nearly the entire sky for transiting planets around nearby stars. While Kepler looked deep into a small patch of space, TESS looks wide and shallow, focusing on stars closer to Earth. This makes its discoveries easier to study with powerful telescopes. Together, these missions form a kind of relay. Kepler showed that the galaxy is full of planets. TESS helps find the ones that are close enough for detailed follow-up. And new telescopes, both in space and on the ground, aim to analyse the atmospheres of these nearby worlds. When you think about Kepler's treasure chest, it is tempting to focus on the most Earth-like candidates, the ones that make headlines and spark imagination. But the true richness of the collection lies in its breadth. It shows us not just what might be familiar, but how varied planetary systems can be. It reveals a galaxy that is not organised around a single template, but full of experiments. Some systems look orderly and spread out. Others are compact and crowded. Some stars host a mix of small and large planets. Others have only small ones, or only giants. Each of these systems adds another data point to our understanding of how planets form and evolve. Each one helps refine our models and challenge our assumptions. As this growing archive of worlds continues to be explored, it naturally leads to deeper questions about what these planets are actually like. Size and orbit are just the beginning. Atmospheres, weather, clouds, and surface chemistry all shape the experience of a planet in ways that are harder to measure, but just as important for habitability. Moving from a catalogue of candidates to a deeper understanding of their environments requires new tools and new approaches. It means reading the light that passes through their atmospheres, looking for the faint fingerprints of molecules. It means modelling how heat moves across their surfaces, how clouds form, and how chemistry unfolds under different kinds of starlight. Kepler's work laid the foundation for all of this. It turned the search for Earth-like worlds into a numbers game, a field where patterns and probabilities could be studied alongside individual cases. Across the growing catalogues of distant worlds, one of the most striking patterns to emerge is not just how many planets there are, but how many of them fall into categories that do not exist at all in our own solar system. We're used to a simple lineup: small, rocky planets close to the Sun, large gaseous giants farther out, a neat division between solid ground and thick clouds of hydrogen and helium. But as astronomers began to measure the sizes and masses of planets around other stars, they found that nature often prefers something in between. These in-between worlds are usually grouped into two broad categories: super-Earths and mini-Neptunes. The names sound straightforward, but they cover a wide range of possibilities, and each possibility carries its own implications for what it might mean to live on, or within such a planet. A super-Earth is, in the simplest sense, a planet that is larger than Earth, but smaller than Neptune. That is a big range. Earth has a radius of about 6,400 kilometers. Neptune's radius is nearly 4 times that. Anything in between might be called a super-Earth, even though the actual experience of standing on the surface, if a surface exists at all, could be radically different from one example to the next. Some super-Earths appear to be scaled-up versions of our own planet. They are dense, suggesting a rocky composition, with gravity perhaps 2 or 3 times stronger than what we feel here. On such a world, mountains might be shorter and broader, pulled down by the stronger gravity. Rivers might flow differently. The atmosphere, if present, could be thicker, held more tightly to the surface. Other super-Earths may be something else entirely. Their density suggests they are not just rock and metal, but also contain large amounts of water, ice, or gas. These could be worlds with deep global oceans, hundreds of kilometers thick, resting on top of high-pressure ice that forms under the immense weight of the water above. In such a scenario, there might be no land at all, no continents, no coastlines, no shallow seas, just an endless expanse of water, with a dark, icy layer at the bottom separating the ocean from the rocky interior. The chemistry of such a world would be very different from Earth's, and the way energy moves through its environment would follow unfamiliar patterns. Mini-Neptunes, on the other hand, are often thought of as smaller versions of Neptune. They are larger than Earth, but not as massive as the gas giants in our own system. These planets typically have thick atmospheres made mostly of hydrogen and helium, surrounding a core that may be rocky or icy. From the outside, a mini-Neptune might look like a small puffy ball of cloud. This surface, if you can call it that, is not something you could stand on. Instead, as you move downward through the atmosphere, the pressure and temperature increase steadily until the gas becomes more like a fluid. Somewhere deep below there may be a solid or liquid core, but it would be buried under thousands of kilometers of dense atmosphere. At first glance, these worlds might not seem like good candidates for life as we know it. The pressures and temperatures in their deep atmospheres could be extreme, but some scientists have wondered whether there might be layers in the atmosphere where conditions are more moderate, regions where temperature and pressure are not too different from what we experience on Earth. In those layers, it is possible, at least in theory, that chemical processes could take place in ways that resemble the beginnings of life. This is a very speculative idea, but it shows how the discovery of these new categories of planets has expanded the range of environments scientists are willing to consider. One of the reasons super-Earths and mini-Neptunes are so interesting is that they appear to be incredibly common. Kepler's data suggests that these mid-sized planets are among the most frequent types in the galaxy. This means that the most typical planetary system might not look like ours at all. Instead of a few small rocky worlds and a few large gas giants, a typical system might be dominated by planets in this middle range. That has implications for how planetary systems form, Current models suggest that these planets may form in regions of the protoplanetary disk, where there is enough material to build a large core, but not enough, or not the right conditions, to accumulate a massive envelope of gas like Jupiter or Saturn. The timing is important. If a core grows quickly while there is still a lot of gas in the disk, it can become a gas giant. If it grows more slowly, or if the gas disperses, it might end up as a super-Earth or a mini-Neptune instead. Migration also plays a role. Planets do not always stay where they form. Interactions with the disk of gas and dust, as well as with other planets, can cause them to move inward or outward over time. This can lead to tightly packed systems of super-Earths and mini-Neptunes close to their stars, like some of the ones Kepler discovered. From the perspective of habitability, this variety raises a lot of questions. On Earth, life is tied closely to the surface. It interacts with the land, the oceans, and the atmosphere in a complex web of feedbacks. On a super-Earth with stronger gravity and a thicker atmosphere, that web might look very different. For example, a thicker atmosphere could enhance the greenhouse effect, trapping more heat and potentially extending the range of distances from the star where liquid water could exist. At the same time, higher pressure at the surface could change the way water behaves. Boiling points would be higher, the density of the air would be greater, sound would travel differently, weather patterns could be more intense or more stable, depending on the specifics. Stronger gravity would also affect the shape of the planet itself. Mountains might be lower, because the crust would have a harder time supporting tall peaks. The planet might be more geologically active, because the increased pressure in the interior could influence how heat moves and how tectonic processes operate. All of these factors could influence how a climate system works over long periods of time. On Earth, the cycling of carbon between the atmosphere, oceans, and rocks plays a key role in regulating temperature. On a super-Earth, those cycles might operate at different speeds or with different balances. Mini-Neptunes present an even more unfamiliar picture. With their thick, hydrogen-rich atmospheres, they might not have a clear boundary between atmosphere and surface. Instead, there could be a gradual transition from gas to liquid to solid as you move downward. In such an environment, traditional ideas about oceans and continents may not apply. If there is a rocky core, it could be surrounded by layers of high-pressure ice or exotic forms of water that only exist under extreme conditions. The chemistry in these layers could be very different from what we see on Earth. Water under high pressure behaves differently. It can form crystalline structures that trap other molecules. These conditions could create environments where complex chemistry takes place in ways we do not yet fully understand. Another possibility that has captured attention is the idea of ocean worlds. These are planets that may be entirely covered in water, with little or no exposed land. Some super-Earths, and even some mini-Neptunes might fall into this category, depending on their composition and history. An ocean world in the habitable zone of a star could, in principle, have a global ocean with a relatively stable temperature. The water would act as a heat reservoir, smoothing out temperature variations between day and night or between seasons. However, without land, some of the processes that regulate Earth's climate might be missing or altered. Weathering of rocks on land plays a role in removing carbon dioxide from the atmosphere. Without that, the balance of greenhouse gases could shift over time. At the bottom of a deep global ocean, the pressure would be immense. If the ocean is deep enough, the water at the bottom might freeze into high-pressure ice, even if the temperature is relatively warm. This ice layer would separate the ocean from the rocky interior, potentially cutting off chemical exchanges between the water and the planet's crust. On Earth, interactions between seawater and the rocky seafloor, especially at hydrothermal vents, are thought to have played a role in the origin of life. If an ocean world lacks this kind of contact, it might have fewer opportunities for the kinds of chemical reactions that lead to complexity. That said, life on Earth has shown an impressive ability to make use of a wide range of environments. It is possible that in a global ocean, different kinds of chemical gradients could form, creating niches for life to exploit. The idea of many shapes of possible homes also extends to the surfaces of these planets, if they have surfaces at all. A super-Earth with a thick atmosphere might have a hazy sky, with clouds made of substances we do not see on Earth. On some planets, clouds could be made of sulfuric acid, methane, or even silicate particles. The colour of the sky could be very different. On Earth, the sky's blue because our atmosphere scatters short wavelength light. On a planet with a different atmospheric composition and a different type of star, the scattering could produce a sky that looks orange, red, or even a deep purple. These visual details are not just cosmetic, they reflect how light and heat move through the atmosphere, which in turn affects climate and habitability. Gravity also shapes how atmospheres behave. On a world with stronger gravity, the atmosphere is pulled closer to the surface. This can make it denser near the ground and thinner higher up. Weather systems might be more compressed vertically, with clouds forming at lower altitudes. On a world with weaker gravity, the atmosphere can extend much farther out into space. This can make it easier for the star's radiation and stellar wind to strip away gases over time, potentially leaving the planet bare. Rotation rate is another factor that can vary widely among these mid-sized planets. Some may rotate quickly, creating strong Coriolis forces that shape wind patterns and ocean currents. Others may rotate slowly or be tidally locked, leading to very different climate regimes. All of these variations mean that when we talk about a super-Earth or a mini-Neptune being potentially habitable, we're not talking about a single, well-defined set of conditions. We're talking about a wide range of possibilities, each with its own challenges and opportunities. This diversity has practical implications for how astronomers search for signs of life. On Earth, one of the most obvious signs of life is the presence of oxygen in the atmosphere. But on a mini-Neptune with a thick hydrogen atmosphere, oxygen might not be a dominant gas, even if life were present in some form. Similarly, the presence of water vapour in the atmosphere might mean different things on different types of planets. On a rocky super-Earth, it could indicate surface oceans or lakes. On a mini-Neptune, it might be part of a thick, steamy atmosphere with no liquid water at the surface at all. Interpreting these signals requires careful modelling and a deep understanding of how different planetary environments behave. The discovery of these many shapes of possible homes has also influenced how scientists think about the origin of life. If life can arise in a wider range of conditions than those found on Earth, then the number of potentially living worlds in the galaxy could be much larger. At the same time, it could be that Earth-like conditions are particularly favourable for the development of complex, long-lasting ecosystems. In that case, super-Earths and mini-Neptunes might host simpler forms of life, or none at all. These are open questions, and answering them will require not just more discoveries, but more detailed observations. This is where new telescopes and instruments come into the story. By studying the light that passes through or reflects off the atmospheres of these planets, astronomers can begin to identify the gases present. They can look for signs of clouds, hazes, and temperature gradients. For some of the closest and most favourable systems, it may even be possible to create rough maps of brightness across a planet's surface, giving hints about where heat is concentrated and how it moves. Each of these measurements adds another piece to the puzzle. Over time, patterns may emerge. Certain combinations of size, mass, atmosphere, and star type might be more conducive to stable, life-friendly conditions. In this way, the growing population of super-Earths and mini-Neptunes serves as a kind of laboratory. Nature has already run countless experiments, creating worlds with different starting conditions and letting them evolve over billions of years. Our job is to observe the results and try to understand the underlying rules. From a broader perspective, this diversity can be oddly comforting. It suggests that the universe is not limited to a narrow set of outcomes. It is willing to explore a wide range of possibilities, from small, rocky worlds like our own to vast, puffy planets wrapped in thick atmospheres. Some of these worlds might be quiet and barren. Others might be chemically active, with complex interactions between their interiors, surfaces, and atmospheres. A few might even be places where something living has found a way to persist. Beneath the long lists of distant planets and the careful categories astronomers use to sort them, there is a particular kind of world that tends to capture the imagination in a quiet, persistent way. Not a rocky landscape with mountains and deserts, and not a puffy sphere of gas with no solid ground at all but something in between. A planet where water does not simply fill valleys and basins, but covers everything. A world wrapped, edge to edge, in a continuous global ocean. These so-called ocean worlds sit at an interesting crossroads in the search for potentially habitable planets. On one hand, water is central to life as we understand it. On the other, a planet that is entirely covered in water might lack some of the features that seem important for long-term stability and chemical diversity. This tension makes them both promising and puzzling at the same time. The idea of a planet with endless seas is not just a product of imagination. Even within our own solar system, there are hints that such environments may exist, hidden beneath layers of ice. Moons like Europa, orbiting Jupiter, and Enceladus, orbiting Saturn, are thought to have vast oceans beneath their frozen crusts. These are not planets, but they demonstrate that water can persist in liquid form far from a star's traditional habitable zone, warmed by internal heat rather than sunlight. When astronomers look at exoplanets, they have found candidates that might take this concept a step further. Planets larger than Earth, with densities that suggest a significant fraction of their mass is made up of water or other volatiles, could be true ocean worlds. Instead of having continents and seas, they might have a single, deep ocean covering the entire surface. To understand how such a planet might form, it helps to think about the early stages of a planetary system. Stars are born from clouds of gas and dust. Around a young star, a disk of material forms made up of tiny grains of rock and ice. Farther from the star, where temperatures are low, water and other volatile compounds can freeze into solid ice. Closer in, those ices evaporate, leaving behind mostly rock and metal. If a planet forms in a region rich in ice, it can accumulate large amounts of water. Over time, it might migrate inward, ending up in a warmer part of the system. The ice melts, and the result is a planet with a global ocean. Alternatively, a planet could form closer to the star and later receive water delivered by icy asteroids or comets from the outer system. This is one of the ideas proposed for how Earth got much of its water. On a larger planet, this process could result in far more water than we have here, enough to submerge any land that might otherwise have risen above the surface. From a distance, an ocean world might look very much like a rocky planet. Its size and mass could place it in the super-Earth category. Its orbit might put it in the habitable zone of its star. The key difference would be hidden beneath the atmosphere, in the depth and extent of its water layer. How deep could such an ocean be? On Earth, the average ocean depth is about 4 kilometers, and the deepest point, the Mariana Trench, reaches nearly 11 kilometers. On a water-rich super-Earth, the ocean could be hundreds of kilometers deep. At those depths, the pressure becomes enormous. Water behaves differently under such conditions. Instead of remaining a liquid all the way down to the rocky surface, it can form high-pressure ice phases, even if the temperature is relatively warm. This ice is not like the ice we are familiar with. It is denser than liquid water, and forms crystalline structures that only exist under extreme pressure. If a layer of high-pressure ice forms between the ocean and the rocky interior, it could act as a barrier. This would prevent direct contact between the liquid water above and the minerals in the crust below. On Earth, this contact is thought to be important for life. At the bottom of our oceans, hydrothermal vents release minerals and heat, creating environments rich in chemical gradients. These places are often cited as potential sites for the origin of life, because they provide both energy and a variety of chemicals in close proximity. On an ocean world with a thick ice layer at the bottom, that kind of interaction might be limited or absent. The ocean would be chemically isolated from the planet's interior. This could make it harder for complex chemistry to develop, or at least change the pathways by which it does, However, it is also possible that life could arise in different ways. Chemical gradients might form within the ocean itself, driven by differences in temperature, pressure, or composition. The upper layers of the ocean might interact with the atmosphere, exchanging gases and energy. The atmosphere of an ocean world would play a crucial role in shaping its environment. A thick atmosphere could trap heat, keeping the surface warm even if the planet orbits toward the cooler edge of the habitable zone. A thinner atmosphere might allow more heat to escape, potentially leading to widespread ice formation at the surface. Clouds would be an important part of this picture. On a planet covered entirely in water, clouds could form over vast areas, reflecting sunlight back into space and helping regulate temperature. The balance between cloud formation and greenhouse warming could determine whether the ocean remains mostly liquid or becomes covered in ice. The rotation of the planet would also matter. A fast-rotating ocean world might have strong currents and weather systems that move heat efficiently from the equator to the poles. A slow-rotating or tidally locked world might have a very different pattern, with a warm region under the star and cooler areas elsewhere. On a tidally locked ocean world, the dayside could be warm and stormy, with constant evaporation and cloud formation. The nightside might be colder, perhaps covered in ice. Between them could be a band of open water, a ring of ocean where conditions are more moderate. These kinds of patterns would shape not just the climate, but also the chemistry of the ocean. Differences in temperature and sunlight could create layers in the water, with different conditions at different depths and latitudes. Sunlight itself would not penetrate very far into a deep ocean. On Earth, most photosynthesis takes place in the upper few hundred meters of the ocean, where light is still available. Below that, the water becomes dark, and life relies on other sources of energy. On an ocean world, this light-filled zone might be a thin shell around the planet, with a vast, dark ocean below. If life exists, it might be concentrated near the surface, where energy from the star can drive chemical reactions. At the same time, if the planet has internal heat, perhaps from radioactive decay or tidal interactions with other bodies, there could be warmer regions deep in the ocean. These might create environments similar to Earth's deep-sea vents, even if the ocean is separated from the rocky interior by a layer of high-pressure ice. In such a scenario, cracks or imperfections in the ice layer could allow some exchange of heat and chemicals. The details would depend on the thickness of the ice, the temperature gradient, and the composition of the water. The presence of salts and other dissolved substances can change how water behaves under pressure. Salty water freezes at lower temperatures and can form different kinds of ice. This adds another layer of complexity to the picture. From the perspective of detection, ocean worlds present both opportunities and challenges. A planet covered in water might have a relatively uniform surface, which could affect how its brightness changes as it rotates. This might be detectable in precise measurements of reflected light. The atmosphere of an ocean world might also show signs of water vapor, clouds, and perhaps other gases that hint at chemical activity. By studying the spectrum of light that passes through the atmosphere during a transit, astronomers can look for the fingerprints of these molecules. However, distinguishing between a rocky planet with oceans and a true ocean world with no land at all is difficult from a distance. Both might show similar signals in terms of size, mass, and atmospheric composition. Density measurements can provide clues. A planet with a lower density than expected for a purely rocky world might have a significant amount of water or a thick atmosphere. But water and gas can produce similar effects on density, making it hard to tell which is responsible without additional information. Some of the candidates identified so far, like certain super-Earths discovered by Kepler and other surveys, fall into this ambiguous category. They could be rocky planets with deep oceans, or they could be mini Neptunes with thick atmospheres. Further observations are needed to clarify their nature. Beyond the technical challenges, there is a broader question about what life on an ocean world might look like. On Earth, the presence of land has played a major role in the evolution of complex life. Plants colonized the land, changing the atmosphere. Animals followed, adapting to a wide range of environments. In a world with no land, this pathway would not exist. Life would remain in the water, perhaps developing complexity in different ways, but without the same opportunities for diversification that land provides. That does not mean such a world would be lifeless or boring. Earth's oceans are full of diverse ecosystems, from sunlit coral reefs to dark deep-sea plains. In some ways, the ocean is a more stable environment than the land, with fewer extreme temperature swings and a constant presence of water. A global ocean might amplify this stability, creating a planet-wide environment where conditions change slowly over time. This could be favourable for the persistence of life, even if the forms it takes are very different from those we are familiar with. The star a planet orbits would shape its ocean world in important ways. A red dwarf's light, rich in infrared, would heat the surface differently than the sun's. The colour and thickness of clouds might change. The depth to which light penetrates the ocean could be affected by the spectrum of the star's radiation. Around a brighter, hotter star, the surface of an ocean world might be warmer, perhaps leading to more vigorous evaporation and stronger weather systems. Around a cooler star, the ocean might be calmer, with large areas of ice near the poles or on the night side of a tidally locked planet. There is also the question of how common ocean worlds might be. Some models suggest that water-rich planets could be quite common, especially around stars that form in regions of the galaxy rich in icy material. If this is true, then the galaxy might contain a vast number of worlds covered in deep oceans, each one a potential habitat for life, even if that life is very different from what we know. This possibility changes the scale of the search. Instead of looking only for planets that resemble Earth, with a mix of land and sea, scientists might need to consider a much broader range of watery environments. At the same time, it raises the challenge of interpretation. If we detect water vapour in the atmosphere of a distant planet, what does that really mean? Is it a sign of a surface ocean, a thick steam atmosphere, or something in between? The presence of water alone does not tell the whole story. The temperature, pressure, and chemical context matter just as much. A planet could have water in many forms, from ice to vapour to liquid, and each form implies a very different environment. Some ocean world candidates might actually be more like steam worlds, with surface temperatures so high that water exists mostly as vapour, forming thick, cloudy atmospheres. These would not be comfortable places for life as we know it, but they still represent a stage in the evolution of a planet's water content. Over time, a planet could move through different phases. It might start as a steam world, cool into an ocean world, and eventually lose some of its water to space or lock it away as ice. The long-term fate of an ocean world depends on many factors, including the star's evolution, the planet's gravity, and the strength of its magnetic field. A strong magnetic field could help protect the atmosphere from being stripped away by stellar winds, preserving the planet's water over billions of years. Without such protection, lighter molecules like hydrogen could escape, gradually drying out the planet. This process might turn an ocean world into a drier, more Earth-like world over time, or into a barren, desiccated one. In this way, ocean worlds might not be a permanent category, but a phase in a planet's life story. A stage that some worlds pass through on their way to becoming something else. From a human perspective, the idea of an endless ocean is both calming and unsettling. There is something soothing about the image of a world covered in water, with gentle waves and a vast open horizon. At the same time, the absence of solid ground can feel disorienting, a reminder of how much of our sense of place is tied to land. These emotional reactions are, of course, reflections of our own experiences. Life elsewhere might not care about land at all. It might find water to be more than enough. As our tools improve, astronomers hope to learn more about these watery worlds. By studying their atmospheres, measuring their temperatures, and looking for signs of clouds and weather, they can begin to distinguish between rocky planets with oceans, true ocean worlds, and gas-rich mini-Neptunes. Each new piece of information helps narrow down the possibilities. Over time, patterns may emerge, showing which types of stars tend to host water-rich planets, and how those planets evolve. This growing understanding also feeds back into our models of how planetary systems form. If ocean worlds are common, it suggests that water and other volatiles are readily available in many protoplanetary disks, and that migration and mixing play a major role in shaping the final distribution of planets. All of this points to a universe that is comfortable with water, not just as a rare, precious substance confined to a few special worlds, but as a common ingredient in the recipe for planets. Whether that abundance translates into an abundance of life remains an open question, but the presence of endless seas on distant worlds expands the range of places where chemistry can unfold in complex ways. Above every solid surface, above every ocean, and even above worlds with no clear boundary between ground and sky, there is a thin, restless layer that tells more about a planet than almost anything else we can measure from far away. This layer is the atmosphere, a shifting envelope of gas that shapes temperature, weather, chemistry, and in many cases, the very possibility of life. When astronomers search for potentially habitable worlds, they often think first about where a planet orbits and what kind of star it circles. But sooner or later, the focus always rises into the sky, because it is there, in the air of a distant world, that the most revealing clues tend to hide. On Earth, the atmosphere feels so ordinary that it is easy to overlook how remarkable it is. We move through it without thinking, breathe it without noticing most of the time, and watch clouds drift across it as part of the background of daily life. Yet, from a planetary perspective, Earth's atmosphere is an active, dynamic system that plays a central role in keeping the planet habitable. The air around us is mostly nitrogen, a relatively inert gas that does not react much with other substances. Oxygen makes up about a fifth of the atmosphere, and that oxygen is largely the product of life itself, released over billions of years by photosynthetic organisms. Carbon dioxide, water vapour, and a handful of other gases make up only a small fraction, but they have an outsized influence on climate by trapping heat and regulating how energy flows in and out of the system. This combination of gases creates a surface environment where temperatures stay within a range that allows liquid water to persist over most of the planet. It also creates pressure at the surface that allows water to behave in familiar ways, forming rivers, lakes, and oceans instead of boiling away or freezing solid. When scientists look at distant planets, they cannot sample the air directly. They cannot scoop up a jar of it or watch clouds form in real time. Instead, they rely on light. Specifically, they look at how starlight changes as it passes through or reflects off a planet's atmosphere. One of the most powerful tools for this is transmission spectroscopy. When a planet passes in front of its star, some of the starlight filters through the thin ring of atmosphere around the planet's edge before reaching our telescopes. Different gases absorb different wavelengths of light. This leaves a pattern of dark lines in the spectrum, a kind of chemical fingerprint. By analysing these patterns, astronomers can identify the presence of certain molecules. Water vapour leaves a distinct signature. So do carbon dioxide, methane, oxygen, and a range of other gases. Each detection is tentative at first, often based on faint signals that require repeated observations to confirm. But over time, a picture begins to form. For some of the larger gas-rich exoplanets, these methods have already revealed atmospheres filled with exotic combinations of gases. Hot Jupiters, for example, have been found to contain sodium, potassium, and even clouds of vaporized rock. These are extreme worlds, far from anything we would consider habitable, but they serve as test cases. They show that we can, in fact, study the air of planets hundreds of light years away. As the focus shifts towards smaller, potentially habitable planets, the challenge becomes much greater. The atmospheres of rocky worlds are thinner and harder to detect. The signals they produce are weaker and more easily drowned out by noise from the star or the instruments. This is where new telescopes come into play. Observatories like the James Webb Space Telescope are designed to detect infrared light with extraordinary sensitivity. Many important atmospheric molecules absorb strongly in the infrared, making this part of the spectrum particularly useful for studying the air of distant worlds. When Webb points at a system like TRAPPIST-1 or one of the nearby planets found by TESS, it can look for the subtle signs of water vapour, carbon dioxide, and other gases in the planet's atmospheres. Each observation is like listening for a whisper in a crowded room. It takes time, patience, and careful analysis to separate the planetary signal from all the other sources of light. Clouds add another layer of complexity. On Earth, clouds play a major role in regulating climate. They reflect sunlight back into space, cooling the planet, but they also trap heat, especially at night, keeping the surface warmer than it would otherwise be. The net effect of clouds depends on their type, altitude, and coverage. Low, thick clouds tend to reflect more sunlight and have a cooling effect. High, thin clouds tend to trap more heat and contribute to warming. On other planets, clouds could be made of very different substances. On Venus, for example, clouds are composed mostly of sulfuric acid. On Titan, Saturn's largest moon, clouds of methane and ethane form and rain down onto the surface. On hot exoplanets, astronomers have detected evidence of clouds made of silicate particles, essentially tiny grains of a rock suspended in the air. On cooler worlds, clouds of water ice or ammonia might be common. These clouds can have a big impact on what we observe. A thick, cloudy atmosphere can block our view of the lower layers, hiding the signatures of gases near the surface. This can make it difficult to determine whether a planet has a thin, Earth-like atmosphere or a thick, gas-rich one. At the same time, the presence of clouds can tell us something about the planet's climate and weather patterns. Variations in brightness as a planet rotates can hint at patchy cloud cover. Changes in the depth of spectral features over time can suggest that clouds are forming and dissipating. All of this adds up to a picture of atmospheres as living systems in their own right. They are not static shells of gas, but dynamic environments shaped by energy from the star, heat from the planet's interior, and interactions with the surface or ocean below. The idea of a breathable sky is, of course, a very human one. When we think about habitability, we often imagine stepping onto a planet and taking off a helmet. But from a scientific perspective, breathability is just one specific outcome of a much broader set of possibilities. Oxygen-rich atmospheres like Earth's are not the only kind that could support life. Early Earth itself had very little free oxygen in its air, yet life existed for billions of years in that low-oxygen environment. Other worlds might host life that uses completely different metabolic pathways, producing and consuming different gases. This is why astronomers are cautious about labeling any particular gas as a definitive sign of life. Instead, they look for combinations of gases that are hard to explain through purely chemical or geological processes. On Earth, the coexistence of oxygen and methane in the atmosphere is one such combination. These two gases tend to react with each other. If there were no ongoing source of both, they would not persist together for long. The fact that they do coexist suggests that something is continually replenishing them. In Earth's case, that something is life. Finding a similar pattern on another planet would be intriguing. But even then, scientists would want to rule out non-biological explanations. For example, certain geological processes or interactions between sunlight and water vapour can produce oxygen without life being involved. The challenge, then, is not just detecting gases, but understanding the context in which they appear. This requires models of planetary atmospheres that take into account the star's radiation, the planet's gravity, its temperature, and its geological activity. Temperature plays a central role here. A planet's atmosphere is shaped by how much energy it receives and how it redistributes that energy. On a hot planet, gases move quickly and chemical reactions happen faster. On a cold planet, things slow down and different compounds may become stable. Pressure is just as important. At higher pressures, gases can behave more like fluids. Chemical reactions can proceed along different pathways. Water, for example, has a wide range of phases under different combinations of temperature and pressure, from familiar ice and liquid to exotic forms of high-pressure ice and supercritical fluid. So when astronomers detect water vapour in the atmosphere of a distant planet, that is just the beginning of the story. They still need to understand whether that water is part of a thin, Earth-like atmosphere, a thick steamy envelope, or something in between. The same goes for carbon dioxide. On Earth, carbon dioxide is a trace gas that plays a key role in climate regulation. On Venus, it makes up the bulk of the atmosphere and is responsible for a runaway greenhouse effect that has turned the planet into a scorching, inhospitable world. A distant planet with a carbon dioxide-rich atmosphere could be anywhere along this spectrum. Without knowing the temperature, pressure, and the presence of other gases, it is hard to say what the surface conditions might be like. This is where multiple lines of evidence become important. By measuring the planet's size and mass, astronomers can estimate its gravity. By studying the star it orbits, they can estimate how much energy the planet receives. By analysing the spectrum of its atmosphere, they can identify some of the gases present. Together, these pieces can be combined into climate models that simulate what the planet's environment might be like. These models are not perfect, and they rely on assumptions based on what we know from Earth and other planets in our own system. But they provide a way to move from raw data to a more intuitive picture of a distant world. Clouds and hazes often turn out to be the wild cards in these models. A planet might, on paper, appear to be in the habitable zone and have the right combination of gases, but if its atmosphere is filled with reflective clouds, it could be much cooler than expected. If it is filled with high, thin clouds that trap heat, it could be much warmer. Hazes, made of tiny particles suspended in the air, can also affect how light moves through the atmosphere. They can mute or hide the spectral signatures of gases, making it harder to detect what the atmosphere is made of. Titan, again, provides a local example. Its thick orange haze hides the surface almost completely in visible light. Only by using infrared instruments and radar have scientists been able to see through it. If a distant exoplanet has a similar haze, our observations might tell us very little about what lies beneath. We might see a mostly featureless spectrum, even if the lower atmosphere contains a rich mix of gases. This uncertainty can be frustrating, but it also highlights how complex and varied planetary environments can be. Even within our own solar system, atmospheres range from the thin, wispy air of Mars to the thick, crushing clouds of Venus, and the deep, turbulent envelopes of the gas giants. Each of these atmospheres is the product of a planet's size, composition, distance from the Sun, and geological history. Exoplanets add even more variety to this list. Some may have lost their atmospheres entirely, stripped away by stellar winds or blown off by intense heating. These would be bare, airless worlds, more like Mercury or the Moon. Others may have thick primordial atmospheres rich in hydrogen and helium, leftovers from the disk of gas that formed the star and planets. These would be more like mini-Neptunes, with conditions at the surface, if a surface exists, that are very different from Earth's. In between lies a wide range of possibilities. Planets with nitrogen-dominated atmospheres like Earth, planets with carbon dioxide-dominated atmospheres like Venus, planets with methane-rich atmospheres like Titan, and perhaps atmospheres made of mixtures we have not yet seen up close. When it comes to the search for breathable skies, it is worth remembering that breathability is a moving target. On Earth, our current atmosphere is the result of billions of years of interaction between life and the planet's geology. It did not start out this way, and it will not remain this way forever. If an alien civilization were observing Earth 1 billion years ago, they would not see an oxygen-rich atmosphere. They might not recognize our planet as a place where complex life exists. This suggests that the window during which a planet has a breathable atmosphere, in the human sense, might be relatively narrow compared to the full lifespan of the planet. So when astronomers look for oxygen or other potential biosignatures, they are not just looking for life. They are looking for life at a particular stage in its history. This adds another layer of chance to the search. A planet might host life for billions of years, but only display obvious atmospheric signs of that life for a fraction of that time. Despite these challenges, progress continues. With each new telescope and each new observation, the sensitivity of our instruments improves. The list of planets with studied atmospheres grows, slowly but steadily. In the coming years, astronomers hope to move beyond simply detecting a few gases. They aim to measure temperature profiles, cloud coverage, and even weather patterns on some of the closest and most favourable worlds. The ultimate goal is to turn these distant points of light into places with personalities. Worlds with warm or cool skies, with cloudy or clear days, with thick or thin air. There is something quietly powerful about that shift. It moves us from thinking of planets as entries in a database to thinking of them as environments, as places where things happen. As you imagine this, you might picture a distant world with a sky that looks nothing like ours. Perhaps it is tinted orange by hazes or darkened by thick clouds. Maybe the star above it is small and red, hanging low and steady in the sky. Or maybe it is larger and brighter, casting sharp shadows across a rocky landscape or a restless ocean. In that sky, molecules are moving, absorbing and emitting light, forming clouds, breaking apart and recombining. The atmosphere is doing its quiet, constant work, shaping the planet's climate and carrying the chemical signals that we, from far away, are trying to read. Understanding those signals is one of the most delicate and demanding tasks in modern astronomy. It requires patience, precision, and a willingness to live with uncertainty. But it is also one of the most promising paths forward, because while we can measure a planet's size and orbit, and even estimate its mass, it is the atmosphere that tells us how the planet actually feels at the surface, warm or cold, dry or wet, calm or turbulent. The next natural question is how these atmospheres and surfaces interact with time itself. How stable are these environments over millions or billions of years? What kinds of events can disrupt them, and how quickly can they recover? Out in the vast spaces between the stars, far from the steady glow of any sun, there are worlds that do not belong to any solar system at all. They wander through the galaxy alone, carrying their own histories with them, shaped not by the light of a star but by the quiet, cold darkness of interstellar space. These are rogue planets, sometimes called free-floating planets, and they represent one of the most unusual and, in some ways, most haunting categories of worlds we have discovered. The idea that a planet could exist without a star to orbit might sound strange at first. In the familiar picture of a planetary system, everything is neatly arranged around a central sun. But the process of planet formation is not always gentle or orderly. Young planetary systems can be chaotic places, with growing planets tugging on each other through gravity, shifting orbits, and sometimes sending smaller worlds flying off into space. When a planet is ejected in this way, it does not simply disappear. It becomes a traveller, moving through the galaxy on its own path, no longer tied to a single star. Over billions of years, these wandering worlds can drift through star-forming regions, pass near other systems, and cross the wide, empty stretches of space between spiral arms. For a long time, rogue planets were more of a theoretical idea than an observed reality. Astronomers suspected they must exist, because computer models of planetary formation often produced them as a natural byproduct. But finding them was another matter. Without a star to light them up, rogue planets are extremely difficult to detect. The breakthrough came through a technique known as gravitational microlensing. This method does not rely on seeing the planet itself. Instead, it takes advantage of the way gravity bends light. When a massive object, like a star or a planet, passes in front of a more distant star from our point of view, its gravity can act like a lens. It bends and focuses the light from the background star, causing it to briefly appear brighter. The exact shape and duration of this brightening can reveal information about the mass of the object doing the lensing. If the lensing object is a star, The brightening can last for days or weeks. If it is a planet, especially a planet not bound to a star, the event is much shorter, sometimes lasting only a few hours. By monitoring millions of stars and looking for these brief flashes of light, astronomers have been able to infer the presence of rogue planets. The results suggest that these lonely worlds may be surprisingly common. Some estimates indicate that there could be as many rogue planets in the galaxy as there are stars, or even more. That means the Milky Way might be filled not just with hundreds of billions of stars and their planetary systems, but also with a vast hidden population of free-floating worlds drifting quietly through the dark. The sizes of these planets appear to vary widely. Some are likely similar in mass to Jupiter, gas giants that were flung out of their birth systems during violent early interactions. Others may be smaller, rocky worlds, perhaps not so different in size from Earth or Mars. Each of these planets carries the memory of a system it once belonged to. A gas giant might have formed far from its star, in a cold, icy region of a protoplanetary disk, before being scattered outward by interactions with other massive planets. A rocky world might have formed closer in, then been ejected during a period of orbital chaos. Once a planet becomes a rogue, its environment changes dramatically. Without the steady input of energy from a star, the surface cools. Any liquid water on the surface would eventually freeze. The atmosphere, if one exists, might condense or collapse onto the surface as ice. At first glance, this sounds like a completely hostile environment, a frozen, dark world with no realistic chance of supporting life. But the story may not be quite that simple. One of the key factors here is internal heat. Planets are not just passive lumps of rock or gas. They can generate heat from several sources. There is the leftover heat from their formation, which can take billions of years to fully dissipate. There is also heat produced by the decay of radioactive elements in the planet's interior. On a large planet, especially a massive gas giant or a super-Earth, this internal heat can be significant. It might be enough to keep parts of the interior warm long after the surface has frozen over. If a rogue planet has a thick layer of ice on its surface, that ice can act as an insulating blanket. Beneath it, there could be a layer of liquid water, kept warm by the heat coming from below. This is similar to what scientists believe exists on moons like Europa and Enceladus, where subsurface oceans are maintained by internal heating rather than sunlight. In this way, a rogue planet could, in theory, carry its own private ocean through the darkness of space, a hidden sea sealed beneath kilometers of ice, isolated from the cold vacuum above. This idea has led some scientists to suggest that rogue planets might not be as lifeless as they appear. If life can exist in subsurface oceans, drawing energy from chemical reactions rather than sunlight, then a free-floating world could still be a potential habitat, even without a star. Of course, this is highly speculative. We do not yet know how likely it is for life to arise in such environments, or how long it could persist. But the mere possibility expands the concept of habitability far beyond the traditional idea of a planet in a habitable zone around a star. The conditions on the surface of a rogue planet would be extreme. Temperatures would likely be close to the background temperature of space, just a few degrees above absolute zero. Unless the planet has a very thick atmosphere that can trap some internal heat, a thick atmosphere, especially one rich in hydrogen, could act as an insulating layer, reducing heat loss. Some models suggest that a rogue planet with a dense hydrogen atmosphere could maintain surface temperatures warm enough for liquid water, even without a star. The hydrogen would trap infrared radiation from the planet's interior, creating a kind of internal greenhouse effect. In this scenario, a rogue planet could, in principle, have a surface ocean and an atmosphere, all powered by its own internal heat. It would be a strange kind of world, with no day or night, no seasons and no sunrise or sunset. The sky would be black, punctuated only by distant stars. Life on such a world, if it exists, would be entirely independent of starlight. Its energy sources would be chemical or thermal, driven by the planet's interior rather than by a sun. The chemistry of such an environment would be very different from Earth's. Without sunlight, there would be no photosynthesis. Instead, life would need to rely on processes similar to those used by some deep-sea organisms on Earth, which draw energy from chemical reactions involving sulfur, hydrogen, or other compounds. These kinds of ecosystems tend to be slower and more limited in scale than those driven by sunlight. The amount of energy available is much lower, which can limit how much life a system can support, but they can be remarkably stable, persisting for long periods of time as long as the chemical energy source remains available. From a detection standpoint, rogue planets are some of the hardest objects to study. Microlensing can tell us that they exist and give rough estimates of their mass, but it does not reveal much about their composition, atmospheres, or internal structure. Direct imaging of rogue planets is possible in a few cases, especially for young, massive ones that still glow with heat from their formation. These planets emit infrared radiation that can be detected by sensitive telescopes. Observations of this kind have revealed a handful of free-floating planetary mass objects in nearby star-forming regions. These young rogues are still warm and bright enough to study in some detail. Astronomers can analyse their spectra to learn about the composition of their atmospheres, looking for molecules like water vapour, methane and carbon monoxide. As these planets age and cool, they become much harder to detect. Their infrared glow fades, and they blend into the cold background of space. Despite these challenges, interest in rogue planets continues to grow. Their apparent abundance suggests that they are a major, though largely unseen, component of the galaxy's planetary population. This raises an interesting question about the total number of potentially habitable environments in the galaxy. If even a small fraction of rogue planets can maintain subsurface oceans or warm surface conditions through internal heating and thick atmospheres, then the number of places where life could exist might be much larger than we would estimate, based only on planets in habitable zones around stars. In that sense, rogue planets blur the boundary between what we traditionally think of as a planet and what we think of as a potential habitat. They show that the presence of a star, while extremely important for many kinds of life, might not be an absolute requirement in every possible scenario. There is also a dynamic aspect to these wandering worlds. Over the course of their journeys through the galaxy, rogue planets can pass near stars. In rare cases, they might even be captured, becoming part of a new planetary system. Such an event would dramatically change the planet's environment. A world that spent billions of years in darkness could suddenly find itself warmed by a star. Ice could melt. Atmospheres could expand. Chemical cycles could begin or resume. If life existed in a subsurface ocean during the planet's time as a rogue, this transition could bring it closer to the surface, perhaps even creating conditions for entirely new kinds of ecosystems. These capture events are thought to be rare, but over the vast timescales of galactic history they are not impossible. They add another layer of complexity to the life stories of planets, showing that a world's environment does not have to be fixed for its entire existence. From a more philosophical perspective, rogue planets invite a different way of thinking about home and belonging in the universe. A planet without a star is, in a sense, truly on its own. It does not participate in the daily rhythm of sunrise and sunset. It does not have a year marked by a journey around a sun. Its passage of time would be marked only by its own rotation, if it rotates at all, and by the slow, gradual cooling of its interior over billions of years. If you were standing on the surface of such a world, assuming you could survive there, the sky would be a deep, unbroken black. Stars would not rise or set. They would simply hang in place, slowly shifting over long periods of time as the planet moves through the galaxy. The absence of a bright central star would make the night sky far more detailed. Faint stars and distant galaxies that are washed out by sunlight on Earth would be visible all the time. The Milky Way might stretch across the sky in a bright, complex band. There is something both peaceful and unsettling about that image. a world without dawn or dusk, without the familiar cycle of light and dark that shapes so much of life on Earth. Yet, in terms of physics, it is just another outcome of the same processes that create stars and planets everywhere. The same gravitational interactions that build systems can also tear them apart, scattering worlds into the void. Rogue planets also provide a kind of natural experiment for scientists. By studying them, astronomers can learn about the extremes of planetary formation and evolution. They can test models of how planets interact, migrate, and sometimes escape. They can also explore how atmospheres and interiors behave when a planet is removed from the influence of a star. How quickly does a planet cool? How does an atmosphere change when there is no incoming starlight? How long can internal heat sustain liquid water? These questions connect to broader themes in planetary science and astrobiology. They touch on the limits of habitability and the resilience of planetary environments. In the context of potentially habitable worlds, rogue planets stand at the edge of the category. They are not in habitable zones. They do not receive steady light from a star. And yet, under certain conditions, they might still host environments where life could exist. This challenges the idea that the search for life should focus only on planets that look like Earth in their orbits and their stars. It suggests that the universe might offer a wider range of settings for life than we initially imagined. At the same time, it underscores how much we still do not know. We have only indirect evidence of most rogue planets. We have not observed their surfaces, sampled their atmospheres, or detected any signs of internal oceans. They remain for now mostly invisible travellers, known to us through brief flashes of light as they pass in front of distant stars, or through faint infrared glows in young star clusters. As technology improves, new surveys and telescopes may be able to detect more of these worlds and study them in greater detail. Missions designed to monitor large numbers of stars for microlensing events will help refine estimates of how common rogue planets really are. Future infrared observatories may be able to directly image more free-floating planets, especially in nearby regions of space, providing data on their temperatures, compositions, and perhaps even their weather patterns if any exist. Each of these advances will help bring these lonely worlds into clearer focus. They will turn what are now mostly theoretical objects into real, characterized members of the galaxy's planetary population. In a broader narrative, rogue planets remind us that not every world fits neatly into the categories we create. Some planets live in crowded systems with multiple neighbours. Some orbit quietly around steady stars, and some drift alone through the dark, carrying their own heat, their own chemistry, and perhaps, in rare cases, their own hidden ecosystems. As we continue to map the galaxy's inventory of worlds, these free-floating planets add depth to the picture. They show that the story of habitability is not just about finding the right place around the right kind of star. It is also about understanding the many ways a planet can generate and retain the conditions needed for complex chemistry. Long before any planet becomes a dot on a chart or a name in a catalogue, it begins its journey to our awareness as a subtle change in light. A fraction of a percent dimmer here, a faint shift in colour there, a brief flicker that lasts only hours before fading back into the steady glow of a distant star. From these almost imperceptible signals, astronomers build entire worlds. They measure their sizes, estimate their masses, and in some cases begin to describe what their skies might be made of. This quiet translation of light into knowledge is at the heart of how telescopes allow us to explore planets we can never visit. At the most basic level, every telescope is a light collector. It gathers photons, the tiny packets of energy that travel across space from stars and planets, and brings them to a focus where they can be recorded by a detector. The larger the telescope's mirror or lens, the more light it can collect, and the fainter the objects it can study. For exoplanets, this is especially important, because planets are almost always much dimmer than the stars they orbit. A star can be billions of times brighter than its planets. Trying to see the planet directly is like trying to spot a firefly next to a searchlight from miles away. Because of this challenge, most of what we know about distant planets comes not from seeing them directly, but from watching how they affect the light of their stars. One of the most widely used methods is the transit technique, which we touched on earlier. When a planet passes in front of its star, it blocks a small portion of the starlight. By measuring how much the star dims, astronomers can determine the planet's size. A larger planet blocks more light. A smaller one blocks less. The timing of these dimming events reveals the planet's orbital period, which tells scientists how far it is from its star, based on the laws of motion and gravity. From this, they can estimate how much energy the planet receives. This method has been extraordinarily successful. Space telescopes like Kepler and TESS have used it to discover thousands of planets. But finding a planet is only the first step. To learn what it is like, astronomers need to look deeper into the light itself. This is where spectroscopy comes in. Light may look smooth and continuous to our eyes, but when it is spread out into a spectrum, it reveals a complex pattern of colours and dark lines. These lines are created when atoms and molecules absorb specific wavelengths of light. Each type of molecule has its own unique pattern, like a barcode. By studying these patterns, astronomers can identify the chemical composition of stars, planets, and the gas between them. When it comes to exoplanets, there are a few main ways to apply this technique. One is transmission spectroscopy, which looks at starlight that passes through a planet's atmosphere during a transit. Another is emission spectroscopy, which looks at the light emitted by the planet itself, often by comparing the combined light of the star and planet to the light of the star alone when the planet passes behind it. A third is reflection spectroscopy, which examines the starlight that bounces off the planet's atmosphere or surface. Each method has its own strengths and limitations, and each reveals different aspects of the planet's environment. Transmission spectroscopy is particularly powerful for studying atmospheres. When a planet transits its star, most of the starlight is blocked by the solid body of the planet, but a small fraction passes through the thin ring of atmosphere around the planet's edge. As this light travels through the atmosphere, certain wavelengths are absorbed by the gases present. By comparing the star's spectrum when the planet is in front of it to the spectrum when the planet is not there, astronomers can see which wavelengths are missing. Those missing wavelengths point to specific molecules. This technique has already been used to detect water vapour, carbon dioxide, sodium, potassium and other gases in the atmospheres of large exoplanets. For smaller Earth-sized planets, the signals are much weaker, but new instruments are pushing closer to the limits of what is possible. Emission spectroscopy takes advantage of the fact that planets are not completely dark. They emit their own light, mostly in the infrared, as heat. When a planet passes behind its star, the combined light from the star and planet suddenly drops by a tiny amount. That drop represents the light that was coming from the planet. By measuring this difference at different wavelengths, astronomers can build a spectrum of the planet's emitted light. This can reveal information about the planet's temperature, and in some cases the composition of its atmosphere. Reflection spectroscopy is similar, but it focuses on the light that a planet reflects from its star. This is most useful for planets that are relatively far from their stars and reflect a significant amount of light. By analysing the reflected spectrum, scientists can look for signs of clouds, hazes, and surface features. All of these techniques rely on incredibly precise measurements. The changes in light caused by a planet can be extremely small, sometimes just a few parts per million. To detect them, telescopes and instruments must be stable and sensitive to an extraordinary degree. This is one of the reasons space telescopes are so valuable for exoplanet research. On Earth, the atmosphere itself absorbs and distorts light. It also produces its own glow and flickers due to turbulence, which can interfere with precise measurements. By placing telescopes above the atmosphere, astronomers can avoid many of these problems. The Hubble Space Telescope was one of the first to make detailed studies of exoplanet atmospheres. Even though it was not designed specifically for this purpose, its stability and sensitivity allowed it to detect water vapour and other gases in the atmospheres of hot Jupiters. The James Webb Space Telescope was built with these kinds of observations in mind. Its large mirror and powerful infrared instruments allow it to study the faint signals from smaller, cooler planets that were beyond Hubble's reach. Webb can observe planets in a wide range of infrared wavelengths, where many important molecules leave their strongest signatures. This makes it particularly well suited for studying potentially habitable worlds, whose temperatures and atmospheric compositions often produce features in this part of the spectrum. Ground-based telescopes also play an important role. Modern observatories use adaptive optics systems to correct for the blurring effects of Earth's atmosphere in real time. By rapidly adjusting mirrors to counteract turbulence, they can achieve sharp images that rival those from space, at least at certain wavelengths. Some of the largest telescopes in the world, with mirrors 8 to 10 meters across, are already capable of directly imaging a small number of large young exoplanets. These planets are still warm from their formation and glow brightly in the infrared, making them easier to see against the glare of their stars. Future telescopes, such as the Extremely Large Telescope and the 30-meter telescope, will have even larger mirrors and more advanced instruments. They may be able to directly image smaller and cooler planets, potentially even some that are similar in size and temperature to Earth. Direct imaging requires specialized equipment called coronagraphs or star shades. These devices block out the light of the star, allowing the much fainter planet to be seen. A coronagraph is built into the telescope, using masks and optics to suppress starlight. A star shade is a separate spacecraft that flies in formation with a space telescope, positioned so that it casts a shadow over the star. Both approaches are technically challenging, but they offer the promise of seeing planets as distinct points of light, rather than just inferring their existence from indirect effects. Once a planet is directly imaged, its light can be spread into a spectrum just like starlight. This opens up the possibility of studying its atmosphere and surface in much greater detail. Even without direct imaging, there are other subtle ways to learn about a planet's surface and atmosphere. One is phase curve analysis. As a planet orbits its star, the amount of its day side that we can see changes, similar to the phases of the Moon. By measuring how the total light from the star and planet changes over the course of an orbit, astronomers can infer how bright the planet is at different phases. This can reveal information about how heat is distributed around the planet. For example, a planet with a thick atmosphere might show relatively small changes in brightness, because heat is transported from the day side to the night side. A planet with little or no atmosphere might show large changes, because the day side is very hot and the night side is very cold. In some cases, this technique has been used to create rough maps of temperature across the surface of hot exoplanets, showing where the hottest and coolest regions are likely to be. Another approach involves looking at how a planet's orbit affects its star's motion. This is known as the radial velocity method. As a planet orbits, its gravity causes the star to wobble slightly. This wobble changes the star's velocity toward or away from Earth, which shifts the wavelengths of its light due to the Doppler effect. By measuring these shifts, astronomers can estimate the planet's mass. When combined with size measurements from transits, this allows them to calculate the planet's density, which provides clues about its composition. While this method does not directly reveal atmospheric information, it is an important part of the overall picture. Knowing whether a planet is dense and rocky or light and gas-rich helps guide interpretations of any atmospheric signals that are detected. All of these techniques generate large amounts of data, often in the form of light curves and spectra that must be carefully processed and analysed. This is where the role of computers and models becomes essential. Raw data from a telescope contains not just the signal from the planet and star, but also noise from the instrument, the environment, and other sources. Scientists use complex algorithms to remove these effects, calibrate the data, and extract the underlying patterns. Once a spectrum is obtained, it must be compared to models of how light interacts with different mixtures of gases at different temperatures and pressures. This process, known as retrieval, involves testing many possible atmospheric compositions to see which ones best match the observed data. The result is not usually a single, definitive answer, but a range of possibilities. For example, the data might suggest that a planet's atmosphere contains water vapor and carbon dioxide, but the exact amounts and temperature profile may be uncertain. This uncertainty is an inherent part of the field. Observations are limited by the sensitivity of our instruments and the distance to the planets. Models are limited by our understanding of atmospheric physics and chemistry, which is based largely on the examples in our own solar system. Despite these limitations, progress is steady. Each new observation adds another point of comparison, another test case for the models. There is also a collaborative aspect to this work. Observations from different telescopes and instruments are often combined to get a more complete picture. A planet might be observed in the infrared by a space telescope, in visible light by a ground-based observatory, and through radial velocity measurements by another instrument. Together, these datasets can provide a more robust understanding than any single method alone. The process of reading the light of faraway planets is, in many ways, an exercise in patience. A single transit might take hours. Multiple transits may be needed to build up a strong enough signal. Some planets have orbital periods of months or years, meaning that opportunities to observe them are rare. This means that studying a single planet can take years of careful planning and observation. Teams of scientists may spend a significant part of their careers focused on a small number of targets, yet the rewards can be profound. The detection of water vapor in an exoplanet's atmosphere, for example, is not just a technical achievement. It is a hint that somewhere, hundreds of light years away, there is a world with water in its sky. The potential detection of oxygen or methane, especially in certain combinations, would be even more significant. It would raise the possibility, however tentative, that life might be influencing that atmosphere. These are not conclusions that scientists rush to make. Extraordinary claims require extraordinary evidence. Any such detection would be scrutinized, repeated, and tested against every possible non-biological explanation. Still, the fact that we can even ask these questions, using light that has travelled across interstellar space, is a testament to how far our tools have come. Looking ahead, there are plans for telescopes specifically designed to search for signs of life on Earth-like planets. Concepts like the Habitable Worlds Observatory and other future missions aim to combine large mirrors, advanced coronagraphs, and sensitive spectrometers to directly image and analyse the atmospheres of nearby rocky planets. These missions would represent a new stage in the exploration of exoplanets. Instead of focusing mainly on discovery and basic characterization, they would aim to conduct detailed surveys of potentially habitable worlds, looking for patterns and outliers. They might reveal, for example, that certain types of stars tend to host planets with similar atmospheric compositions, or that certain planetary sizes and orbits are more likely to produce stable, life-friendly climates. They might also reveal surprises, worlds that do not fit our expectations and challenge our theories. Throughout all of this, the fundamental process remains the same. Light leaves a star, it interacts with a planet, it travels across space, it enters a telescope, it is recorded by a detector, and then, through careful analysis and interpretation, it becomes knowledge. This chain of events, stretching across light years and years of human effort, is what allows us to turn distant points of light into places with temperatures, skies, and, potentially, histories of their own. As we continue to refine these methods, the picture of the galaxy's planetary population becomes more detailed and more nuanced. We move from knowing that planets exist, to understanding what kinds of planets are common, to exploring what those planets might actually be like. If we can read the light of faraway planets well enough, can we find signs that something living has left its mark there? Somewhere between the precise measurements of light curves and the careful modelling of distant atmospheres, there is a quieter, more open-ended question that lingers in the background of almost every discussion about potentially habitable worlds. It is not a question that can be answered with a single spectrum or a single discovery. It is a question that unfolds slowly, across decades of observation and debate. Are we alone, or are there other places in the galaxy where chemistry has crossed the line into something living? Astronomers rarely ask this question directly in their scientific papers. Instead, they talk about biosignatures, habitability, and atmospheric disequilibrium. These are technical terms, but behind them is a simple idea. Life, if it exists, tends to change its environment in ways that are hard to ignore. It takes in energy, processes matter, and releases waste. Over long periods of time, these activities can leave traces in the air, the water, and the surface of a planet. On Earth, this is easy to see in hindsight. The atmosphere we breathe is not just a product of volcanoes and sunlight. It has been shaped by life itself. Early in our planet's history, the air contained very little free oxygen. The oceans were filled with dissolved iron, and the surface was a very different place from what we know today. Then, billions of years ago, photosynthetic organisms began to release oxygen as a byproduct of their metabolism. At first, that oxygen was quickly absorbed by the oceans and rocks, but eventually the sinks filled up, and oxygen began to accumulate in the atmosphere. This event, often called the Great Oxidation Event, transformed the planet. The rise of oxygen allowed for the development of more complex forms of life. It also changed the chemistry of the atmosphere and the surface in ways that would be visible from far away. If an alien astronomer had been watching Earth before and after this transition, they would have seen a clear, dramatic shift in the composition of the planet's air. This idea, that life can imprint itself on a planet in a detectable way, is the foundation of the search for quiet signals of life on distant worlds. The most commonly discussed of these signals is oxygen. On a rocky planet, free oxygen is highly reactive. It tends to combine with other elements and compounds. If it is present in large amounts in an atmosphere, something must be continuously producing it. On Earth, that something is life. Plants, algae, and certain bacteria split water molecules during photosynthesis, releasing oxygen into the air. However, oxygen can also be produced by non-biological processes. For example, ultraviolet light from a star can break apart water vapor in a planet's upper atmosphere, releasing hydrogen and oxygen. The hydrogen, being lighter, can escape into space, leaving oxygen behind. This means that the presence of oxygen alone is not a definitive sign of life. Astronomers have to consider the context. What kind of star does the planet orbit? How much ultraviolet radiation does it receive? What is the planet's gravity and temperature? This is why researchers often focus on combinations of gases rather than single molecules. On Earth, the simultaneous presence of oxygen and methane is particularly interesting. These two gases tend to react with each other. In a purely chemical environment, they would not coexist in large amounts for long. The fact that both are present in Earth's atmosphere suggests that there are ongoing processes replenishing them. In Earth's case, those processes are largely biological. Finding a similar combination on another planet would be intriguing, but even then, scientists would proceed with caution. They would look for alternative explanations, such as unusual geological activity or chemical reactions driven by the star's radiation. Another potential biosignature is nitrous oxide, a gas produced by some microorganisms on Earth. It has a strong spectral signature and is less likely to be produced in large amounts by non-biological processes. However, detecting it on a distant planet would be extremely challenging with current technology. There are also ideas about surface biosignatures. On Earth, vegetation reflects light in a distinctive way, particularly in the near-infrared. This is sometimes called the red edge. If a distant planet had widespread plant-like organisms, it might show a similar feature in its reflected light. This is a more speculative approach, because it assumes that life elsewhere would use pigments and photosynthetic processes similar to those on Earth. But it illustrates how the search for life is not limited to gases in the air. It can extend to the way a planet's surface interacts with light. At the same time, scientists are careful not to let Earth's example overly constrain their thinking. Life elsewhere might use different chemistry, different energy sources, and different environmental niches. It might not produce oxygen at all. It might produce gases we do not yet recognize as significant. This leads to a broader concept sometimes called agnostic biosignatures. These are patterns in data that suggest the presence of complex self-sustaining processes, even if we do not know exactly what those processes are. One example is atmospheric disequilibrium. This refers to a situation where the composition of a planet's atmosphere is far from what would be expected if it were in chemical balance. Certain combinations of gases, if left alone, would react with each other until they reached a stable state. If they remain in an unstable mix, something must be actively maintaining that state. On Earth, life is that something. It continuously produces and consumes gases, keeping the atmosphere in a state of imbalance. Measuring disequilibrium on a distant planet is difficult because it requires precise measurements of multiple gases and an understanding of how they interact under that planet's specific conditions. But it offers a way to look for life without assuming it works exactly like life on Earth. Another approach focuses on temporal changes. Life is dynamic. It grows, spreads, and responds to its environment. On Earth, this leads to seasonal changes in atmospheric composition. For example, carbon dioxide levels fluctuate as plants grow and die back with the seasons. If astronomers could detect similar periodic changes in the atmosphere of a distant planet, it might suggest the presence of large-scale biological activity. Detecting such changes would require long-term monitoring and extremely sensitive instruments. It would also require disentangling biological effects from purely physical ones, such as changes in cloud cover or volcanic activity. Volcanoes themselves are an important part of this story. They can release large amounts of gases into the atmosphere, including carbon dioxide, sulfur dioxide, and even methane. These gases can mimic some of the signals that might otherwise be attributed to life. A planet with intense volcanic activity could have an atmosphere that looks, at least in some respects, like it is being influenced by biology. This is another reason why context is so important. Scientists need to consider a planet's geological activity, its age, and its internal heat when interpreting atmospheric data. The star also plays a central role. Different types of stars emit different kinds of radiation, which can drive chemical reactions in a planet's atmosphere. A red dwarf, for example, emits relatively little ultraviolet light compared to a sun-like star, but it can produce intense flares that deliver bursts of high-energy radiation. These flares can break apart molecules in the atmosphere and trigger chemical pathways that would not occur under steady illumination. Over time, this can shape the composition of the air in ways that are hard to predict. This means that a biosignature around one type of star might not look the same around another. A planet orbiting a red dwarf might have a very different atmospheric chemistry from a similar planet orbiting a G-type star, even if both host life. Because of all these variables, the search for life is often framed as a search for patterns rather than proofs. A single gas detection is rarely enough to draw strong conclusions. Instead, scientists look for a consistent set of observations that, taken together, point toward a biological explanation as the most plausible. This layered approach is sometimes compared to building a legal case. Each piece of evidence on its own might be ambiguous, but when multiple independent lines of evidence all point in the same direction, the overall picture becomes more convincing. In practical terms, this means combining measurements of atmospheric composition, temperature, pressure, and even surface properties. It means understanding the star's behavior and the planet's orbit. It means modeling the planet's climate and geology. Only by considering all of these factors can scientists begin to assess whether a particular signal is more likely to be the product of life or of non-biological processes. The quiet nature of these signals is part of what makes the search so challenging. We are not looking for radio messages or flashing beacons. We are looking for slight imbalances in the chemistry of a distant atmosphere, tiny shifts in the way a planet reflects light, or subtle changes in a spectrum over time. These are whispers rather than shouts. They require patience and careful listening. There is also a human dimension to this work that often goes unspoken. The search for life on other worlds is not just a technical challenge, it is also an emotional and philosophical one. Every potential biosignature carries with it the weight of expectation. The possibility, however remote, that we might be seeing the influence of something living on another planet touches on deep questions about our place in the universe. This is why scientists are so cautious. The history of astronomy includes moments where exciting claims were later revised or retracted. The canals of Mars, the supposed signals from pulsars that were briefly nicknamed Little Green Men, the early reports of possible fossilized life in Martian meteorites. Each of these episodes serves as a reminder of how easy it is to let hope run ahead of evidence. Modern astrobiology has learned from these experiences. It emphasizes rigorous testing, independent verification, and transparency about uncertainties. When a new potential biosignature is reported, it is typically framed as a candidate, not a discovery. Other researchers are encouraged to examine the data, test alternative explanations, and attempt to reproduce the results with different instruments or methods. This process can be slow and sometimes frustrating, but it is designed to ensure that any eventual claim of life beyond Earth is as robust as possible. There is also an awareness that the first clear detection of life elsewhere, if it happens, will likely be subtle rather than dramatic. It may come in the form of a spectrum that shows an unexpected combination of gases or a pattern of variation that cannot be easily explained by known physical processes. It may take years of additional observation and analysis before the scientific community reaches a consensus on what that signal means. In the meantime, the search itself continues to shape how we think about life and planets. It encourages us to look at Earth from a different perspective, as a planet among many, with its own particular combination of conditions and history. This planetary perspective has influenced fields beyond astronomy. It has shaped our understanding of climate, ecology, and the long-term future of our own world. By studying how atmospheres and climates might evolve on other planets, scientists gain insights into the processes that shape Earth as well. The search for life elsewhere also invites us to consider how life might respond to different environments. On Earth, life has found ways to survive in places that once seemed utterly inhospitable. Deep in the ocean, near hydrothermal vents, high in the atmosphere, buried in rock, frozen in ice. These extremophils expand our sense of what is possible. They suggest that life, once it begins, can adapt to a wide range of conditions. This adaptability is part of what makes the search for life on other planets so open-ended. Even if a world does not look like Earth in terms of temperature, pressure, or chemistry, it might still host some form of life that we have not yet imagined. At the same time, there are limits. Physics and chemistry impose constraints on what is possible. Certain conditions, such as extremely high temperatures or the absence of any stable energy source, make it difficult for complex, long-lasting systems to exist. Understanding where those limits lie is an active area of research. It involves studying not just planets, but also the fundamental properties of molecules, reactions, and energy flows. In this way, the search for life becomes a bridge between astronomy, chemistry, biology, and physics. It draws on insights from all of these fields and in turn feeds back into them. As new telescopes come online and new missions are launched, the range of worlds we can study in detail will expand. Nearby stars will be surveyed for Earth-sized planets. The atmospheres of those planets will be probed for chemical signatures. Some of these worlds will likely turn out to be barren or hostile. Others may have conditions that are, at least in some respects, similar to Earth's. The possibility that one of them might show a compelling sign of life remains, for now, an open question. It is a possibility that sits quietly at the edge of our data, neither confirmed nor ruled out. There is a certain calm in that uncertainty. It reminds us that we are still in the early stages of a long process of discovery. The galaxy is vast, and our tools, though powerful, are still limited. Every spectrum we analyse, every light curve we study, is a small step toward a deeper understanding of the worlds around us. Each one adds a piece to the broader picture of what kinds of planets exist and what kinds of environments they host. In the end, the question of life on other worlds is not something that will be answered by a single observation or a single generation of scientists. It is a question that unfolds over time, shaped by incremental progress and occasional leaps forward. As we listen for these quiet signals in the light of distant stars, we're also, in a way, listening to the universe itself, trying to learn how common or how rare the phenomenon of life might be. After travelling through so many distant systems, wandering past stars both quiet and restless, and listening closely to the faint chemical whispers of faraway skies, it can feel natural to turn your attention back towards something familiar. Not in a sudden or abrupt way, but gently, as if your gaze is slowly drifting from the deep background of the galaxy back toward the small, warm point of light that marks our own place within it. This shift in focus does not diminish the vastness we have just explored. If anything, it makes it more tangible. Our planet, our star, and our small corner of the Milky Way become part of a much larger pattern, one that includes countless other worlds, each with its own conditions, histories, and possibilities. Earth often feels, in daily life, like a complete and self-contained place. The sky arches overhead. The ground stretches out beneath our feet. The horizon marks the edge of what we can see, but in a cosmic sense, Earth is a traveller, moving through space at tremendous speed, orbiting the Sun, which itself orbits the centre of the galaxy along with billions of other stars. This motion is usually invisible to us. The night sky appears mostly the same from one year to the next. The constellations hold their shapes. But over longer timescales, even these patterns change. Stars drift relative to one another. New stars are born, and old ones fade. In that slow, ongoing movement, our solar system is not an isolated island. It is one of many systems scattered through the spiral arms of the Milky Way, each one a potential home for planets, and in some cases perhaps for life. When astronomers talk about the galaxy being full of neighbours, they do not mean this in a casual or metaphorical sense. Based on what we have learned from missions like Kepler and TESS, planets appear to be common. Most stars seem to host at least one planet. Many host several. This means that in the region of space around us, within just a few dozen light years, there are likely hundreds or even thousands of planets. Some are large and gaseous, some are small and rocky, some orbit close to their stars, others move along wide, slow paths. A fraction of these planets, perhaps a significant one, may lie in regions where temperatures allow liquid water to exist, at least under the right conditions. These are the worlds that often capture the most attention, because they overlap with what we know about life on Earth. But even among these potentially habitable candidates, there is immense variety. Some orbit red dwarfs, under dim reddish light. Others orbit stars more like our Sun, with brighter, whiter skies. Some may be wrapped in thick atmospheres. Others may have thin air or none at all. Some might be ocean worlds, covered in deep global seas. Others might be dry, with only small amounts of water locked away as ice or vapour. Some might be geologically active, with volcanoes and shifting surfaces. Others might be quiet and ancient, their landscapes unchanged for billions of years. This range of possibilities can feel almost overwhelming. It suggests that there is no single template for what a potentially habitable world looks like. Instead, there is a spectrum, a wide and varied set of environments that all fall under the broad umbrella of places where complex chemistry, and perhaps life, could exist. Turning back to Earth in this context can be a grounding experience. Our planet has its own particular combination of features that make it what it is. The size and mass that give it just the right gravity to hold onto an atmosphere without becoming a gas giant. The distance from the Sun that allows water to remain liquid over long periods. the presence of a magnetic field that helps protect the atmosphere from being stripped away by solar winds. There are also factors that are less often highlighted but no less important. The presence of a large moon, which stabilizes Earth's axial tilt and helps regulate long-term climate. The plate tectonics that recycle carbon and other elements between the surface and the interior. The oceans that store heat and distribute it around the globe. Each of these features plays a role in shaping Earth's long-term habitability, and while some of them may be common on other planets, others might be relatively rare. This does not mean that Earth is unique in every respect. It does mean that the particular combination of circumstances that led to the world we know is one outcome among many possible ones. As our understanding of exoplanets grows, this idea becomes more concrete. We can point to specific systems and say, this one has multiple rocky planets in the habitable zone. This one has a super-Earth with a thick atmosphere. This one has a tightly packed family of worlds around a small, cool star. Each of these systems represents a different way that a planetary system can organize itself. Each one is a reminder that the processes that formed our own solar system are not the only way to build a collection of worlds. From a broader perspective, this diversity suggests that the galaxy is not just full of planets, but full of planetary stories. Each world has a history that includes its formation, its early interactions with its star and its neighbours, its geological evolution, and the long-term changes in its atmosphere and surface. Some of these stories may include the emergence of life, others may not. But even a lifeless world can be complex, shaped by physics and chemistry, in ways that are interesting in their own right. There is also a sense in which the search for neighbours is not just about finding life, but about understanding context. By studying other planets, we gain a better understanding of Earth. For example, by comparing Earth's atmosphere to those of Venus and Mars, scientists have learned a great deal about how different evolutionary paths can lead to very different outcomes, even for planets that start out relatively similar. Venus and Earth are close in size and likely formed from similar materials. Yet today, Venus is a world of crushing pressure and extreme heat, with a thick carbon dioxide atmosphere and clouds of sulfuric acid. Mars, on the other hand, is cold and thin-aired, with much of its original atmosphere lost to space. These contrasts highlight the importance of factors like distance from the star, planetary mass, and magnetic fields. They also show how small differences early in a planet's history can be amplified over time. When we add exoplanets to this comparison, the range of outcomes becomes even wider. We see worlds that are hotter than Venus, colder than Mars, heavier than Earth, lighter than Mercury, and everything in between. This expanded context can change how we think about habitability. Instead of viewing it as a simple yes or no property, it becomes something more like a continuum, a set of conditions that can be met to different degrees, in different ways. A planet might be habitable in the sense that liquid water can exist on its surface, but only in certain regions or at certain times. Another might have stable conditions over most of its surface, but lack some of the chemical ingredients we think are important for life. Another might have all the right ingredients, but only for a relatively short window of time. This layered view of habitability makes the search for life both more challenging and more interesting. It suggests that there may be many worlds that are, in some sense, close to being like Earth, but not quite the same. It also suggests that if life is common, it might exist in a wide range of forms and environments, not just on planets that closely resemble our own. From a human point of view, this can be both comforting and unsettling. Comforting because it implies that Earth is part of a larger family of worlds, rather than a solitary outlier. Unsettling because it raises the possibility that there are places where life has followed a completely different path, shaped by conditions we can only partially imagine. At the same time, it is important to remember how little we actually know. Even the most well-studied exoplanets are still, in many ways, just points of light and lines in a spectrum. We infer their properties from careful measurements and models, but we do not see their landscapes, feel their weather, or experience their skies directly. There is a layer of abstraction between us and these distant worlds that cannot be fully removed with current technology. This gap between data and experience leaves room for imagination, but it also calls for humility. Our interpretations are based on the best information we have, but they're always subject to revision as new data becomes available. The history of astronomy is full of examples where new observations overturned long-held assumptions. The idea that the Milky Way is just one galaxy among many, the realization that planets are common around other stars, the discovery of planets in places where we did not expect them, such as tightly packed systems or extreme orbits. Each of these shifts has expanded our understanding of what is possible. Looking forward, it is likely that future observations will continue this pattern. We may find planets with atmospheric compositions that challenge our models. We may find systems with arrangements that do not fit neatly into our current categories. We may even find a planet with a combination of signals that strongly suggest the presence of life, though interpreting such a finding will require great care. In the meantime, the idea of a universe full of neighbours remains a hypothesis supported by growing but still incomplete evidence. We know that planets are abundant. We know that many of them exist in regions where liquid water could, in principle, be present. We know that some of them have atmospheres that we can begin to study in detail. What we do not yet know is how often life actually emerges, how long it tends to persist, and how likely it is to leave detectable traces. These unknowns are not obstacles so much as invitations. They point toward the kinds of questions that future missions and future generations of scientists will try to answer. From a more personal perspective, there is something quietly grounding about placing Earth within this broader picture. Our planet is not the centre of the universe. It is one world among many, orbiting one star among billions. At the same time, it is the only place we know for certain that supports life. That fact gives it a special significance, not in a cosmic sense, but in a human one. Understanding how rare or how common life might be elsewhere can deepen our appreciation for the world we inhabit. It can highlight the fragility of the conditions that make it possible for complex ecosystems to exist. This awareness has practical implications. Studying planetary climates and atmospheric evolution on other worlds can inform our understanding of climate change on Earth. It can help us see which processes lead to stable, long-term habitability and which lead to runaway effects or irreversible shifts. In this way, the search for neighbours is not just an outward-looking endeavour, it is also a way of learning more about home. There is also a sense of continuity in this exploration. The same tools and techniques used to study distant exoplanets are often applied to our own solar system. Spacecraft study the atmospheres of Mars and Venus. Probes explore the oceans hidden beneath the ice of moons like Europa and Enceladus. These local investigations and distant observations inform each other. What we learn about water, chemistry, and geology in our own backyard helps us interpret the signals we see from faraway worlds. Likewise, the diversity of exoplanets can inspire new ways of thinking about the potential environments within our own system. As you let these ideas settle, it can be helpful to imagine the Milky Way not as a collection of stars on a map, but as a vast three-dimensional space filled with systems, each one with its own architecture of planets and moons. Some of those systems may be quiet and stable, with worlds moving along predictable paths for billions of years. Others may be more dynamic, with planets migrating, colliding, or being ejected into interstellar space. Within this complex web of motion and change, Earth follows its own path. It has its own history, marked by the formation of oceans, the rise of life, mass extinctions, and periods of rapid change. In the grand scheme of things, this history is just one of many. Other worlds, if they host life, may have stories that are equally rich and equally shaped by their own particular circumstances. The idea that the universe might be full of neighbours does not necessarily mean that we will ever meet them. The distances between stars are vast. Even the nearest potentially habitable exoplanets are many light years away. Travelling to them with current or foreseeable technology would take timescales far beyond a human lifetime. Communication, too, is constrained by the speed of light. A signal sent to a star 10 light-years away would take 10 years to arrive, and another 10 years for any reply to come back. These realities place practical limits on what contact might look like, even if life is common. Yet, the absence of direct contact does not diminish the value of knowing. The knowledge that we are part of a galaxy filled with worlds, some of which may be capable of supporting life, can reshape how we think about our place in the cosmos. It can foster a sense of connection, not in a literal sense, but in the recognition that the same physical laws and chemical processes that operate here also operate elsewhere. From that perspective, the search for neighbours becomes a way of understanding the universe as a whole. It is an exploration of how matter organises itself into stars and planets, how energy flows through systems, and how complexity can arise under the right conditions. As this exploration continues, each new discovery adds another thread to the tapestry. A new planet here, a new atmosphere there, a new system that defies expectations. These threads do not form a complete picture yet, but they hint at a pattern of richness and variety that extends far beyond what we can currently observe in detail. Returning to the idea of home, it can be comforting to think of Earth as part of this larger family of worlds, not isolated, but connected through the same cosmic processes that shape stars, planets, and galaxies. This connection does not require that life be common or rare. It exists simply in the shared origin of everything we see. The atoms in our bodies were forged in the interiors of stars long before the sun was born. The water in our oceans was delivered by icy bodies that formed in the early solar system. The air we breathe is the product of both geological processes and the activity of living organisms over billions of years. In this sense, Earth is already a meeting place of cosmic history and biological evolution. As you hold that idea, it becomes possible to see the search for potentially habitable planets not just as a technical project, but as part of a broader human curiosity, a desire to understand how common our experience might be and how it fits into the larger story of the universe. This curiosity does not demand immediate answers. It is content for now with careful steps and gradual progress. Each observation, each model, and each new piece of data adds a little more clarity, even if it also reveals new questions. The galaxy remains vast and in many ways mysterious, but it is no longer an empty stage with a single inhabited world at its centre. It is a place filled with planets, systems, and possibilities. As this understanding settles in, there is a gentle sense of perspective that can come with it. Our world is small in a cosmic sense, but it is not alone in being a world. Whether the universe is full of life or only sparsely inhabited, it is certainly full of planets, each one a product of the same fundamental forces that shaped Earth. And as we continue to look outward, reading the light of distant stars and the faint signals of faraway worlds, we're also, in a quiet way, learning more about ourselves and the place we call home. There is no final answer yet, no definitive statement about how many neighbours we truly have. There is only an ongoing process of exploration, one that unfolds over time, guided by curiosity and careful observation. In that process, the journey itself becomes as important as the destination. The act of looking, of measuring, of imagining what might be out there, connects us to a universe that is far larger and more varied than the everyday view from our own sky might suggest. And as this sense of connection grows, it leaves room for a simple, steady thought to linger. Whatever else the galaxy may hold, we are part of it. One world among many, moving through space, under the light of one star, in a universe that continues to reveal its depth, one quiet signal at a time.